At the beginning of autumn in the year 25, on the outskirts of our solar system, an extraordinary and alarming scene unfolded, causing astronomers around the world to seriously ponder what was happening with the interstellar visitor named 3I Atlas. Unlike familiar comets, which typically follow predictable orbits and display characteristic tails, this object began to behave as if it were something other than a simple celestial body moving along an interstellar path. A few days ago, scientists observed it approaching the Sun to a distance of just 2 astronomical units, which is roughly 2 different distances from Earth to our star, and at that moment, its behavior changed radically. Contrary to all previous expectations and models, its brightness suddenly increased, and it began to shine much more intensely than predicted. Surprisingly and alarmingly, its atmosphere appeared to swell to half the diameter of our Sun, transforming into a massive, blazing sphere emitting a bright, saturated green glow. Moreover, a tail appeared, directed straight toward the Sun, which seemed impossible for a comet, as tails usually extend away from the heat and light source. Scientists were at a loss. How could this happen? This interstellar guest, rushing at a speed estimated to exceed that of ordinary comets, was becoming increasingly mysterious with each passing hour, less resembling a familiar celestial body and more like something else, a cosmic enigma demanding urgent answers. The countdown to its crossing of the hypothetical Geliolene, an imaginary point where it might intersect Mars' orbit, had begun, and with each hour, this alien and mysterious celestial body became more unpredictable. It was transforming from an ordinary comet into something extraordinary, and all researchers observing this event understood. We are facing a new, unexplained phenomenon that requires explanation. At this moment, the question arises, what does this news mean for all our knowledge of space, interstellar bodies, and the nature of the universe itself? What happens when chemistry, which seems alien and extraterrestrial, finally awakens and manifests in such a bright and unusual form? The beginning of this astonishing event was recorded in mid-September of the year 25. At that time, astronomers, carefully monitoring 3I Atlas, noticed something troubling in their data. Their brightness measurements began to show an increase exceeding all possible predictions and models. Initially, the readings rose from the expected 16 to 12 or 14, which in itself represented a significant jump. For those unfamiliar with the peculiarities of the astronomical scale, it should be clarified, in astronomy, magnitudes work in reverse order. The smaller the number, the brighter the object. Therefore, increasing the brightness value from 6 to 12 or 14 is equivalent to a decrease in the numerical indicator, meaning that the object has become 6 times brighter than previously assumed. If such an increase occurred gradually, in this case, a rapid, accelerating growth was observed. Research databases specifically designed for tracking comets, the so-called COPS project, began recording astonishing trends. The brightness levels of this interstellar visitor were constantly rising above expectations. Observations made with telescopes and specialized instruments confirmed that 3I Atlas did not fit into existing models. It exceeded all the scenarios that astronomers had created to calculate its trajectory toward the Sun. Moreover, a critical moment occurred when this object approached the Sun to within about 2 astronomical units, roughly 93 million miles, which happened in earlier mid-September. For comparison, Earth is about 1 astronomical unit away from the Sun. Frequent bright flashes in the sky often serve as a signal of high instability characteristic of cosmic objects. This is especially true for comets, which can undergo fragmentation during sudden gas and dust outbursts, breaking into many smaller pieces or forming impressive clouds of debris, like cosmic storms raging in their atmospheres. These processes happen very quickly, and as a result, a comet can exhaust its volatile reserves in a very short period, leading to its rapid darkening and disappearance from visible horizons. It is no wonder that some astronomical models predicted its behavior differently, and the fact that 3I Atlas became brighter than calculations forecasted indicates the presence of processes in nature that scientists do not yet fully understand. Such astonishing phenomena remind us of how much remains mysterious and unexplored in space, despite all the achievements of modern science. However, despite these remarkable discoveries and the unpredictable behavior of the comet, there is no need to panic. This is not a cause for concern regarding a threat to Earth. The scientific community, primarily representatives of NASA, confirmed that 3I Atlas maintains a safe distance from our planet, never approaching closer than 1 full astronomical unit. This distance is about twice the distance from Earth to the Sun, completely ruling out the possibility of a collision or any significant threat. The main concern is more about our understanding of the processes occurring, rather than an immediate danger to life on Earth. We observe how this interstellar object, like a cosmic time capsule, undergoes radical changes as it approaches the inner part of the solar system. And it is worth considering the possible consequences of this event. This object, originating from a debris disk around another star, may be located very far away, hundreds of light years from us. It was formed from materials that have never experienced the warmth of our Sun, never been subjected to conditions typical of our planetary system. These materials are rare and unique, as until now they remained in a stationary and unchanged state deep within cold interstellar space. And now, for the first time in its existence, this interstellar visitor is encountering the intense radiation environment of our inner solar system. The sudden increase in brightness observed in its behavior could indicate the start of a reaction that awakens internal chemical processes, which have remained dormant for millions or even billions of years. Perhaps, for the first time in the history of this object, its exotic ices, formed in extremely low temperature conditions, are beginning to evaporate, having remained stable and unchanged in the icy depths of interstellar space. These ices, formed under extremely cold conditions, may now start to sublimate under the influence of solar radiation, something previously impossible. As a result, we may witness the unveiling of chemical signatures preserved in pristine form from other star systems, revealing unique features that have been stored in our galaxy since ancient times. The timing of this event creates a sense of urgency, as scientists have limited time to study and understand what is happening. The 3 Atlas is approaching several important dates that will determine what exactly astronomers will be able to learn by observing this unprecedented guest. First, it will reach its closest approach to Mars, just 30 million kilometers away, allowing orbiting spacecraft around the red planet to capture the tiniest details invisible from Earth's surface. Then, by the end of October, specifically on the 29th and 30th, the comet will reach its perihelion, the closest point in its path to the Sun, approximately between 16 and 1 astronomical unit away. It is at this moment that a tense turn of events begins for Earth-based observers. As the 3 Atlas approaches our star, we rely on the mechanical eyes of satellites and interstellar spacecraft scattered throughout the solar system, especially those orbiting Mars, to observe what could become the most exciting manifestation of interstellar chemistry in human history. These devices, constantly monitoring the cosmos, enable us to detect even the slightest changes and anomalies in the behavior of unusual objects. The increasing brightness recorded by their sensors indicates that the comet or other interstellar guest is not planning to quietly pass beyond the boundaries of our system without causing any noise. Current observations indicate that this object is likely energized through interaction with our Sun, possibly approaching the moments of flares or other intense events that could shed light on its internal structure and composition, which had previously remained hidden. But an important question arises: will these discoveries occur during the weeks when Earth's telescopes are overwhelmed by bright sunlight, making observations difficult or even impossible? Data collected in September paint a picture of an object in a transitional stage, making it even more mysterious. The measured brightness levels, exceeding preliminary calculations and models, suggest that Atlas, as this object is tentatively called, has already transformed into something different from its state during its long journey through interstellar space. The question emerges: is this simply a natural stage in the development of a comet within the framework of an unusual, exotic body, or are we encountering something entirely unprecedented in our experience with visitors from other star systems? In the coming minutes, we will try to understand why the coma of this cosmic traveler extends farther than expected, why its tail points toward the Sun rather than away from it, and how its recent transition to a sinister green glow might indicate chemical processes never before observed in interstellar visitors. With each new brightness measurement, mysteries deepen, yet it remains crucial to understand exactly what we are dealing with, since 3ALS. These are not just any random comet, but the third confirmed interstellar guest in human history. Its behavior already clearly shows that each interstellar object possesses its own unique set of rules and characteristics. The second part of our story is dedicated to the discovery and classification of this unusual body. It all began atop a mountain in Chile, where robotic systems with mechanical precision scan the night sky, creating images that baffle even experienced observers. On July 1, 2025, early warning systems for possible asteroid collisions, so-called ATLAS, detected a faint spot of light moving among the stars. Initially, it was interpreted as another small space object, a minor comet or asteroid. However, this modest observation soon completely changed our understanding of interstellar visitors. What truly makes an object interstellar is not only its origin beyond our system but also the mathematical confirmation that it can never be gravitationally bound to the orbit of our Sun. Its trajectory, a so-called hyperbolic path, is characterized by such velocity and energy that after completing its orbit around the Sun, it will continue moving forever, drifting further and further away, permanently leaving the boundaries of our system. Mathematical precision in orbital calculations is relentless. This object is moving too quickly for the gravity of our star to capture it. The designation, Tri-Atlas, speaks for itself, tri, because it is the third confirmed interstellar object in human history, and Atlas, as an abbreviation of interstellar. That is why its behavior already raises many questions and debates among scientists. What unique chemical and physical processes are occurring inside this body, and why? Its predecessors, one Oumuamua asteroid discovered in 2017 and two interstellar objects found in 2019, each amazed scientists with their uniqueness and unusual characteristics that did not fit into traditional classifications. These discoveries not only expanded the boundaries of our understanding of space but also constantly reminded us of the complexity astronomers face when searching for and studying such rare interstellar bodies. In this context, it can be said that Tri-Atlas continues this trend, demonstrating that interstellar objects remain some of the most unpredictable and mysterious elements of the universe. The process of their detection is a real challenge for modern technologies and methods, as capturing and recognizing such bodies is still incredibly difficult and requires high precision and patience. The Rio Hurtado Observatory, located in the arid Atacama Desert in Chile, is part of a global system designed to detect potentially hazardous asteroids that could approach Earth. This system takes a series of quick images of the same patch of sky over very short intervals and then applies complex computer algorithms to identify everything moving against the background of stars. It was on such a clear July night that the skies over the Chilean desert brought a sensation. A faint, barely noticeable trail appeared on the screens, barely distinguishable from thousands of other objects, asteroids, comets, and space debris constantly present in our inner solar system. Even when these images were taken, earlier photographs showed that this object, later named Tri-Atlas, had already been in astronomical databases for several weeks. This meant that its existence had been recorded long before anyone realized its true nature and potential significance. Such a delay in recognition is quite typical when discovering interstellar bodies, as in their early stages they appear as ordinary asteroids, which only later develop characteristic comet features, fuzzy atmospheres and tails resulting from the sublimation of ice under the influence of solar heat. Initial estimates indicated that we were dealing with a dim comet surrounded by a soft cloud, resembling an atmosphere, which immediately suggested that this object was much larger than a simple rocky asteroid. Unlike rocky bodies, comets develop such diffuse gaseous envelopes as they approach the Sun, when solar heat causes sublimation of ice, resulting in an expanding gas-dust atmosphere. In the case of 3I Atlas, a discovery located well beyond the third astronomical unit from the Sun, the presence of such features indicated that it contains volatile substances capable of evaporating even in the coldest, outer regions of our system. When news of this discovery spread within the astronomical community, large telescopes began directing their gaze toward the new interstellar visitor. The Hubble Space Telescope, which was operated in July, captured detailed images of the object, while the Very Large Telescope in Chile and other ground-based observatories conducted additional observations, broadening our understanding of its nature. These subsequent studies revealed that 3I Atlas is a much more complex and intriguing body than initial images suggested. Its size estimates remain quite uncertain, a common challenge when studying such distant and faint objects that are nearly impossible to measure directly. Updated data obtained in August with Hubble narrowed the possible core diameter range to between 32 and 56 kilometers. This spread highlights the difficulties in precisely distinguishing the solid core from the surrounding dust coma, a sparse gas dust cloud. The uncertainty in size is significant because it directly impacts calculations of mass, density, and structure. Currently, the interstellar object named 3I Atlas is moving through space at a speed of approximately 130 miles per hour. Or, converting to more familiar units, about 58 kilometers per second. This velocity greatly exceeds any typical speeds of objects naturally occurring within our solar system. For comparison, Earth, orbiting the Sun, moves at about 30 kilometers per second, which is much slower. At the same time, the speed of a comet approaching its perihelion will continuously increase under the influence of solar gravity, potentially reaching 68 kilometers per second or more, equivalent to over 150 miles per hour. These velocity figures clearly indicate the extraterrestrial nature of this cosmic visitor, as no object born within our solar system can reach such speeds without the aid of gravitational maneuvers around massive planets, which use gravity as a means of acceleration. The interstellar object, named 3I Atlas, carries a unique kinetic signature of its interstellar origin, accumulated over millions of years of its journey through the galaxy. During this time, it moved under the influence of the gravitational fields of stars and the rotation of the galaxy itself, making it a truly unique phenomenon for science. To date, there have been very few confirmed interstellar visitors in our solar system, and each new discovery becomes a valuable contribution to the development of astronomical knowledge. Until 2017, scientists only had theoretical models explaining how such objects might behave during interstellar travel and how they interact with their environment. One of the most notable examples was the astronomical object, Oumuamua, which challenged many previous assumptions with its unusual elongated shape and mysterious acceleration that could not be explained by gravitational effects. Another example is 2I Borisov, which appeared more traditionally shaped like a comet, yet its chemical composition was surprisingly different from anything observed in our solar system. Now, the appearance of an object called 3I Atlas adds a third significant data point to this limited collection of interstellar visitors, and preliminary studies suggest it will be as unique as its predecessors. The behavior of this object raises new questions and challenges existing models, especially due to its unexpectedly large cometary shape and unusual brightness evolution. Each interstellar body seems to bring its own set of physical and chemical characteristics, indicating a much greater diversity of small body formation processes in our galaxy than previously assumed. Determining the type of this cosmic body involves not only confirming its interstellar origin but also establishing which category it belongs to, an asteroid, a comet, or something entirely different. The presence of cometary features suggests a similarity in behavior to such bodies, while spectroscopic analysis of the gases and dust composition will help understand how this object formed and evolved within its original stellar system. This interstellar object is not a typical comet ejected from the Oort cloud, which serves as a frozen reservoir periodically sending visitors into the solar system. Instead, 3I Atlas formed around another star, originating from materials subjected to entirely different conditions, varying temperatures, pressures, and chemical environments from those characteristic of our local cosmic environment. It represents a direct example of the processes that occurred during planet formation in other systems, possibly billions of years ago. Trajectory calculations show that it is moving along a path that will provide scientists with unique opportunities for observation, especially during its closest approach past Mars, which is planned. This particular orbital geometry is not accidental. The inclination of the interstellar object's trajectory and its temporal parameters of orbital movement create conditions under which spacecraft orbiting planets or traveling through interplanetary space find themselves in the most advantageous position to observe it precisely when ground-based telescopes on Earth's surface lose sight of it due to the bright solar reflection. However, simply knowing which side this interstellar visitor came from and where it is headed is not enough for a full understanding of what we are observing. The real mysteries lie in how it behaves upon its first encounter with the solar radiation emitted by our star, and why its behavior deviates so significantly from all existing theoretical models and predictions. Part 3. Trajectory and Timeline. The time for the 3ATS and for astronomers eager to unravel its secrets is steadily shrinking before it disappears into the bright solar glare. Orbital mechanics calculations have helped create an accurate map of its path through the inner regions of the solar system, highlighting key dates that could become turning points in understanding this unique interstellar object. These dates are not just points on a timeline but important milestones that determine what humanity can learn by observing this guest from interstellar space. The first of these is October 23, 2025. On this day, the 3ATS will pass by Mars at a distance of approximately 30 million kilometers, which corresponds to about 1/10 or slightly less than 2 astronomical units. In cosmic terms, this is an extremely close approach, placing the interstellar visitor within the range of radio and optical systems monitoring the red planet. This event would serve as a crucial reference point, offering a unique opportunity to obtain the clearest and most detailed data about the nature of this object. But it is precisely at this moment that difficulties begin. As soon as the 3ATS reaches its closest approach to Mars, providing spacecraft with the clearest and most detailed images, ground-based telescopes on Earth begin to lose the ability to track it. The rigid geometry of orbital mechanics increasingly complicates observation as the object gets closer to the Sun in the sky, creating conditions under which it becomes practically invisible due to the bright solar illumination. At the end of October, specifically on the 29th and 30th, the 3ATS will reach the so-called perihelion, the point at which it will be located just inside the average orbital distance of Mars, at a distance of approximately 14 to 16 astronomical units. This distance is slightly less than the radius of Mars's orbit, exposing the interstellar visitor to the most intense solar radiation, which differ significantly from the conditions it experienced while traveling through the galaxy and approaching our solar system. It is precisely during this period that observers on Earth encounter the greatest difficulties in tracking and studying it. The evolution of this interstellar object's velocity tells its own dramatic story. Currently, it is moving at a speed exceeding tens of kilometers per second. At the moment of reaching perihelion, it will attain its maximum velocity, which, according to calculations, may approach 68 kilometers per second, roughly equivalent to 152,000 miles per hour. For comparison, our planet, orbiting the Sun, moves at an average speed of about 30 kilometers per second. Therefore, this interstellar guest will be traveling more than twice as fast as our entire planet, making its movement not just an impressive fact but a crucial demonstration of the physical laws governing interstellar travel. These speeds are not merely statistical figures. They open a window into the deep mechanisms underlying the motion. Like many other interstellar objects, this one bears clear signs of accumulated kinetic energy, which was stored during its long journey through the vast expanses of interstellar space. This energy is generated by the enormous velocities at which it moves, with each kilometer per second representing colossal distances traveled along the interstellar road, constantly influenced by gravitational fields of numerous stars, as well as the rotation of the galaxy itself. Consequently, its trajectory approaching our solar system occupies a special place in astronomical calculations and observations. In particular, its path is aligned so that it moves near the ecliptic plane, the plane in which the main planetary orbits lie, and this positioning significantly increases the likelihood of collision with planets such as Mars. In the future, it may also create conditions for a closer approach to Jupiter, expected around the year 2026. Regarding the geometry of this approach, it is important to emphasize that it is not a random coincidence. Objects approaching from various points in three-dimensional space generally follow quite random trajectories, and the probability that they will pass so close to multiple planets during a brief transit through our system is very low. That is why, despite initially being classified as potentially hazardous, security concerns related to its approach have never become a serious matter of worry. The closest approach to Earth will occur at a distance of approximately 1 to nearly 2 astronomical units, which is twice the average distance between Earth and the Sun. This means it is well beyond any probable threat to our planet. This confirmation from NASA assures that the distance is safe, completely alleviating public concerns about a potential collision and allowing astronomers to shift their focus from planetary defense to studying the scientific aspects of this unique object. However, scientists face another equally important challenge: observational geometry. From early October to early November of this year, Triatlas is in what is called the superior conjunction phase, a period when its position in the sky relative to Earth makes it too close to the Sun. As a result, the solar elongation, the angular distance between the object and the solar disk as seen from Earth, decreases to less than 30 degrees for most of this critical period. Imagine trying to spot a firefly hovering next to a bright spotlight, and you will understand how difficult observation becomes under such conditions. Even the most advanced and powerful telescopes cannot distinguish the faint glow of this interstellar body from the blinding brightness of our Sun illuminating the sky. When two objects are very close to each other on the celestial sphere, it creates serious limitations for ground-based astronomy, and during such periods, the most active manifestations of the comet may remain virtually invisible to our observational instruments. This presents a fundamental paradox in the encounter with Triatlas. As solar heating reaches its peak and the comet likely undergoes the most dramatic transformations, such as intense gas emission or even fragmentation, its activity generally becomes difficult to observe from Earth's surface. At this moment, the peak of gas release occurs, and events like the formation of extensive tails or nucleus fragmentation can reach their maximum intensity. However, it is precisely during these weeks, when the comet appears brightest and most active, that ground-based telescopes are unable to observe it fully due to unfavorable conditions. This noticeable gap in observations underscores the importance of space-based spacecraft within the solar system. This is especially relevant for satellites orbiting Mars, such as the European Space Agency's missions. After the perihelion, when the comet reaches its closest point to the Sun, the timeline based on calculations and observations provides a clear and quite realistic picture of what astronomers and enthusiasts can expect when observing this cosmic visitor. In particular, there is a hypothesis that if three interstellar objects, including the comet, are able to survive their close approach to the Sun without significant damage, then observations from Earth could resume as early as November or early December. During this period, the solar elongation, that is, the angle between the direction to the object and the line connecting Earth and the Sun, will reach such values that it will fall outside the conditions necessary for observations with ground-based instruments. However, by that time, the comet is likely to rapidly fade in brightness, since most of its volatile material, which could produce a bright glow, has already been exhausted during the heating peak, which, unfortunately, will remain inaccessible for direct observation. Brightness forecasts based on calculations indicate that even at its brightest, when the comet reaches its maximum, it will remain a telescopic object, visible only through magnifying devices. Its magnitude is estimated to fluctuate in the range of 11th to 12th magnitude. Such brightness levels are too faint to be seen with the naked eye, but are quite accessible to amateur astronomical instruments such as small telescopes or binoculars. The absence of a bright, spectacular glow visible without instruments may disappoint casual observers or those hoping for a spectacular sight. However, this in no way diminishes the scientific value of this unique astronomical event, as it presents an opportunity to obtain unprecedented data on this interstellar comet, the first of its kind to appear in our solar system. Regarding the motion dynamics, the velocity profile of the comet reveals another important aspect of the timeline. As it approaches perihelion, the closest point to the Sun, its speed continues to increase under the influence of solar gravitational acceleration. This is a classic effect observed in all objects moving within a star's gravitational field. However, immediately after passing perihelion, when the comet begins to recede from the Sun, the same gravitational field starts to slow it down, gradually reducing its velocity. This change in speed significantly affects the duration of the peak heating phases and the time frames during which the comet remains observable with systems on Earth and in near-Earth orbit. Beyond perihelion, trajectory calculations show that this interstellar comet will continue its journey through the solar system, gradually moving away from the Sun. Ultimately, by March 2026, it will approach Jupiter. Although this approach will occur at a significantly greater distance than during the flyby of Mars, it will still provide additional opportunities for observation by spacecraft. During this period, the comet will begin its final exit from our solar system, opening new horizons for scientific research. The created timeline thus reveals a narrow window of opportunity, similar to nothing previously encountered in the history of astronomy. Unlike traditional periodic comets, which return to the Sun at regular intervals and allow scientists to study their properties multiple times, the interstellar comet has only one chance to be the subject of a primary and unique investigation, as it has come from another star system. To achieve the most valuable results, all observational activities, timeframes, and spacecraft capabilities must align as precisely as possible. Only then can humanity extract the fullest and most valuable scientific information from this rare astronomical event. Within our solar system, an astonishing object is observed, a comet whose outer layer, composed of carbon dioxide, has stretched to an incredible length, about 34,888 kilometers. To grasp the scale of this measurement, consider this. This thin, ghostly atmosphere of the comet extends roughly halfway across the diameter of our bright, shining Sun. Such a size truly boggles the mind, as it significantly exceeds the dimensions of most known comet tails and envelopes. The comet, tentatively designated as 3ATS, has become so enormous and expanded that its atmosphere occupies a space equal to the entire orbit of Mercury, the planet closest to the Sun. As a result of this formation, a vast bubble of gas and dust has formed, surpassing all known similar structures observed around other comets in our solar system. This phenomenon is unique and unprecedented in the history of cometary astronomy, as such an event has never been recorded or documented before. The formation of this comet occurs for a very specific reason. When solar radiation reaches the nucleus of the body, it heats the ice contained inside. This ice, composed of frozen carbon dioxide and water, begins to sublimate, transitioning directly from a solid to a gas, bypassing the liquid phase. This sublimation process is not just a gradual evaporation but rather an explosive transition, during which the frozen materials inside the nucleus literally burst outward, releasing particles of dust, larger fragments, and a mass of gas into the surrounding space. As a result, an expanding atmosphere is formed, capable of reaching enormous sizes, creating an impressive gas bubble around the comet. Visual observations and spectroscopic studies suggest that the composition of this comet, especially in its outer shell, tells a story about the conditions in which it formed. In particular, the dominance of carbon dioxide over water vapor indicates that the object originated in a region where temperatures were low enough for carbon dioxide to freeze and settle, while water remained primarily in vapor form. This significantly differs from the conditions typical for the formation of most comets in our solar system, where water is often the main volatile component. Considering the origin of this comet in the context of processes occurring in the distant interstellar space, it can be hypothesized that it formed in a region where temperatures remained consistently very low, possibly in the outer layers of a protoplanetary disk around another star. In such areas, temperatures were low enough for carbon dioxide to condense freely and form solid ice, while water mostly existed as vapor, creating a carbon dioxide-rich environment. This reflects the chemical and physico-chemical conditions present during its birth and formation. In most known comets of our solar system, water is the primary volatile substance, with carbon dioxide playing a secondary role, not dominating the composition. The inverse ratio observed in comet 3ATS indicates the conditions under which it formed. likely in a region with low temperatures and high pressure, different from those typical of our system. But it is not only the composition that makes this comet unique. Visual data obtained from the Hubble Space Telescope, as well as ground-based observatories, reveal structures that cast serious doubt on existing notions of comet behavior. Usually, it is expected that a comet will have a prominent tail directed away from the Sun, caused by solar radiation pressure that pushes gas and dust in the direction away from the star's light. However, in the case of Comet 3ATS, something different is observed. Instead of the usual tail pointing away from the Sun, it exhibits what is called an anti-tail, a stream of material that, subsequent observations made with the Gemini South Telescope on August 27, confirmed continues to persist and even develop. This fact indicates that the anti-tail, distinguished by its structure, is not a random or temporary anomaly but a stable feature inherent to this body. Scientific understanding of the processes underlying the formation of the anti-tail involves complex mechanisms beyond simple solar radiation pressure effects. For example, large dust grains with significant mass cannot be easily pushed away by solar photons because the radiation pressure force is insufficient to displace them. However, these particles can maintain trajectories directed toward the Sun if they were ejected from the nucleus at a sufficiently high initial velocity and with a specific direction. It is also necessary to consider the projection effect. Moving three-dimensional material observed from Earth at a certain angle may appear to be moving directly toward the Sun, complicating the interpretation of observed structures. Nevertheless, existing theoretical models struggle to explain the stability and pronounced brightness of the so-called solar jet, designated as 3ATLS. The structure appears too well-defined, sharply outlined, and persistent for its formation to be the result of simple projection effects. At the same time, the sizes of dust grains and the velocities of their ejection required to produce such an extensive anti-tail exceed the physical capabilities acceptable for cometary nuclei. Recent studies suggest that an anti-tail could form due to unusual rotational states of the nucleus or unique surface properties characteristic of interstellar objects. For instance, slow rotation of the nucleus can sustain temperature gradients between its day and night sides, promoting the concentration of gases in specific directions. It is also believed that the surface composition of the 3ATLS object may include materials that respond to solar heating in unusual ways, different from those typical of comets observed within our solar system. Additionally, the expansion velocity of the coma adds another dimension to this complex puzzle. Spectroscopic studies show that gas velocities in the coma exceed typical values for comets at similar distances from the Sun. This enhanced gas release indicates the sublimation of supervolatile substances that remain stable only in interstellar space conditions. The rapid sublimation of these substances upon initial solar heating causes the coma's temperature, measured via infrared methods, to exhibit anomalous readings. This suggests the presence of heating mechanisms beyond simple solar radiation absorption. Possible explanations include chemical reactions occurring between previously separated compounds or energy release from structures formed under interstellar conditions, such as in icy crystals containing exotic components. Three-dimensional modeling of the coma structure, based on data obtained from various viewing angles and across different wavelength ranges, reveals asymmetries indicating uneven gas emission from the surface of the nucleus. Unlike well-studied comets, which exhibit relatively symmetrical and calm structures, the object 3IATLC displays bright jets and fans of material emanating from specific regions of its nucleus. These features indicate that the surface of this nucleus contains distinct areas rich in volatile substances, which may have been exposed as a result of impact events, thermal cycles, or other processes that occurred during its interstellar journey. Such emission characteristics suggest the presence of localized zones with increased concentrations of volatile components, which in turn points to a complex history of formation and evolution in the interstellar medium. The model designed to analyze the released gases is capable of preserving vital information about the conditions under which the comet formed, as well as its subsequent evolution over millions of years, during which it slowly but steadily traveled through the vastness of space. The study of dust particles within the comet's coma allows researchers to determine their size distribution, which often differ significantly from similar data obtained for comets within our solar system. The detection of a substantial fraction of large dust grains, necessary for the formation of the prominent anti-tail structure, suggests that the triad either formed under different conditions with a different dust-to-ice ratio than typical local comets, or that the particles comprising it have undergone significant alterations due to interstellar processes during its long interstellar voyage. The comet's expansion dynamics show temporal fluctuations that are not coincidental but are likely related to its velocity away from the Sun, and possibly to its rotation periods. As the triad approaches perihelion, the point of closest approach to the Sun, its coma continues to grow and become more complex, reaching larger sizes due to increasing solar heating, which causes ice sublimation and gas ejection. Modeling the further evolution of the comet, necessary for predicting its future changes, faces unprecedented challenges. This is due to the unusual composition of the coma, its complex geometry, and the elevated gas emission rates, all of which require significant adjustments to standard comet physics models. Scientists are effectively compelled to develop new theoretical approaches in real time, as each new observation continues to reveal unexpected and sometimes astonishing phenomena that had not been previously considered. The implications of these discoveries extend far beyond the study of a single comet. If interstellar comets exhibit such unusual characteristics in their comas, it may mean that our current understanding of the physics of these objects, primarily based on data from comets originating within our solar system, provides only a very narrow view of the possible phenomena. Each such interstellar traveler has the ability to challenge our fundamental assumptions about how these objects are formed and the paths they follow through space. As the triad approaches critical points of convergence with both Mars and the Sun, further changes in its coma, including its expansion and structural evolution, will become crucial tests of existing theories. These processes will allow us to evaluate their validity in practice and determine which model most accurately describes what is happening. The question is whether the most significant changes will occur during a period when telescopes on Earth are temporarily unable to track the comet's behavior, the so-called observational gap, when data collection will be limited. However, it is important to remember that the evolution of the coma is only one aspect of the overall transformation of the triad as it encounters intense solar radiation. The most noticeable and astonishing change recorded by scientists was the appearance of a bright green glow that emerged around mid-September. At that moment, the entire comet began to shine with a rich green hue, indicating chemical processes previously unseen in this interstellar visitor. This entire transformation became a true event, sparking waves of interest and discussion among astronomers worldwide. The color change did not occur immediately or gradually but suddenly, with a vivid emerald radiance that seemed to illuminate the entire surface of the comet. This bright green glow gave it the appearance of a living organism, as if it had suddenly come to life against the backdrop of endless starry darkness. For untrained observers, this change was barely noticeable. The comet remained too faint to be seen with the naked eye. However, sensitive cameras mounted on telescopes around the world began to capture the phenomenon. The transformation in the comet's visual appearance, especially evident in photographs taken during the lunar eclipse on September 14, was truly impressive. That evening, the moon's shadow obscured part of the sky, making it noticeably darker and creating an ideal background to highlight the comet's new, bright glow. Thanks to this contrast, it became possible to observe and record its unusual green radiance, which seemed to tell its own unique story written in the language of quantum mechanics and molecular chemistry. At the core of this magical glow is a process in which certain molecules in space absorb ultraviolet rays from the Sun, causing electrons within these molecules to jump to higher energy levels. When these electrons return to their original, lower energy state, they begin to emit light at precisely defined wavelengths, which human eyes perceive as a vivid green radiance. If we speak specifically about the comet known as 3I Atlas, then most likely, the source of its green glow is diatomic carbon molecules, that is, two-atom carbon compounds linked together in the form of molecules, which are represented in chemical notation as C2. Such diatomic carbon in space behaves like a kind of molecular neon sign, brightly shining in the vast dark abyss of interstellar space. Under the influence of solar ultraviolet radiation, these molecules, especially those containing an additional element, sulfur, forming the compound C2S, begin to emit light at wavelengths approaching approximately 516 nanometers. It is this range that creates the characteristic green glow, making Comet 3I Atlas one of the brightest and most spectacular observed in recent years. This process, known as fluorescence, essentially involves converting invisible solar energy into visible light capable of traveling millions of kilometers so that ground-based telescopes can detect it. But it is precisely here that a mystery arises, one that remained unresolved for a long time. Initial spectroscopic observations of Comet 3I Atlas showed very little evidence of carbon-containing compounds in its composition. Chemical analysis conducted in early autumn revealed that the comet's atmosphere is dominated by gases such as carbon dioxide and water vapor, with trace amounts of carbon molecules, usually responsible for the green glow of comets, being found in very small quantities. This contradiction, on the one hand, a bright green luminescence, and on the other, an almost complete absence of the corresponding compounds in its chemical makeup, became a real puzzle for researchers. They began to wonder what was happening in the expanding atmosphere of this comet, as it was clear that some processes were occurring that caused the appearance of green color despite the low concentration of the supposed sources of this glow. One possible explanation was the hypothesis of phase transitions occurring in the behavior of gases and dust released from the comet's nucleus. When the comet approached the Sun and reached a distance of 2 astronomical units in early September, solar heating began to act very actively on the internal deposits within the nucleus. These carbon-rich materials, which had remained trapped inside for a long time, possibly experienced sublimation for the first time in their history, a process where solids transition directly into gas under the influence of heat. As a result of this sudden release of carbon-rich substances, previously inaccessible to space observations, new chemical reactions began to occur, causing the bright green glow. The timing of these changes coincided with a period of rapid increase in the comet's brightness observed in mid-September, and it is quite likely that these two events are interconnected. It is possible that the visible green glow, which is sometimes observed in the coma of interstellar objects, often raises many questions and hypotheses. One of the possible causes of this phenomenon is thought to be the mixing of emissions originating from various types of molecules, as well as from carbon-containing molecules that are unique to the interstellar medium. These molecules differ from those found in comets of the solar system and exist in interstellar space under conditions that vary significantly in composition and concentration. The complexity also lies in the fact that the sensitivity of the instruments used, as well as the data processing methods, introduce a certain degree of uncertainty in accurately determining the color of this glow. Different telescopes equipped with various filters and image processing systems may interpret the same object differently, producing slightly different shades. For example, what appears distinctly green in one image may seem more blue-green or even yellow-green in another, depending on the specific wavelengths recorded and the methods used to combine them into final color images. Interest in the evolution of the green glow is significant because it provides additional clues to understanding the chemical composition and processes occurring in the coma. Unlike stable emission expected from simple molecular fluorescence processes, the observed variations in the intensity and distribution of the green color indicate a dynamic nature of this phenomenon. In some regions, the intensity of the green emission is significantly higher than in others, serving as evidence that carbon-containing molecules are not evenly distributed within the expanding gas cloud. Such inhomogeneous distribution is likely related to localized gas ejections occurring at specific points on the comet's nucleus. In these cases, jets of material erupting from particular surface areas of the nucleus may have different chemical compositions, affecting the emission characteristics. Alternatively, variations in the light could reflect chemical transformations within the coma caused by exposure to solar ultraviolet radiation. This radiation can break down complex organic molecules, converting them into simpler components that fluoresce at different wavelengths, thereby creating a changing green hue. Additionally, the green glow serves as an important diagnostic tool for assessing the physical conditions inside the coma. The intensity of molecular fluorescence directly depends on parameters such as molecular density, temperature, and the intensity of solar ultraviolet radiation. By analyzing how the brightness of the green emission varies with increasing distance from the nucleus and over time, scientists can construct a three-dimensional map of the distribution of carbon-containing gases within the coma. Temperature measurements based on the characteristics of green emission indicate that carbon-containing molecules are in thermal equilibrium with the other gases composing the comet. This suggests an efficient transfer of energy between different molecular species, which in turn points to a high collision frequency and active gas dynamics within the expanding atmosphere. The appearance of green glow in interstellar comets, such as 13 ATC, is becoming an increasingly important marker, broadening our understanding of the differences between interstellar objects and those originally belonging to the solar system. For example, the object known as Oumuamua showed no signs of bright cometary activity, and consequently, no changes in its color. In contrast, the object Dwi Boris exhibited more typical cometary colors, dominated by shades of blue and white scattered sunlight rather than molecular emission lines. Finally, the object IATL became the first interstellar body observed with a classic green cometary glow, the very feature that astronomers and enthusiasts associate with the approach of periodic comets. Although the wavelengths and intensity of green emission in this comet may differ slightly from those of familiar comets, these differences could be a crucial key to understanding its unique chemical composition. Nuances such as minor spectral deviations might indicate the presence of substances previously found only in objects formed in other, foreign stellar systems. Therefore, monitoring the change in the comet's color at different points in its trajectory becomes particularly valuable and requires regular, precise measurements. As the 3 astronomical trans comet approaches the Sun and gradually becomes invisible from Earth's surface, there is a need for careful monitoring of its condition as soon as possible. In early October, when the green emission related to molecular fluorescence may continue to intensify or, conversely, disappear entirely, it is important to record its maximum. The peak intensity of this green glow typically occurs near the perihelion, the point at which solar heating reaches its maximum. However, precisely at this critical moment, the comet finds itself in a state where most ground-based telescopes will be unable to observe it. It will be hidden behind the Sun's side, and access to its spectrum will be limited. Spectroscopic observations conducted afterward aim to identify the specific molecules responsible for this unusual green emission. This requires the use of highly powerful telescopes with high resolving capabilities, as well as ideal weather conditions, which are becoming increasingly difficult to achieve as the comet approaches the solar glare. Every clear and warm evening sky becomes a precious event for astronomers, who rush to capture and record the emission characteristics before the object disappears from view. This transformation into a bright green glow is an event that surpasses mere visual admiration. It serves as direct evidence that the 3 AFS are undergoing significant chemical changes under the influence of solar radiation. Molecules that activate and glow in the comet's coma likely remained chemically inert for millions of years, existing in a state of frozen repose as they traveled through interstellar space between different star systems. And now, for the first time since their formation, this interstellar visitor begins to ignite, as solar energy awakens chemical processes that have remained dormant since the comet's birth in another stellar system. The green glow thus becomes a kind of awakening of alien chemistry, a sign that the comet, having entered our system, is undergoing transformation. Initial signs of molecular activity in materials formed under conditions possibly different from those in our solar system begin to manifest. However, observing this process is a challenging task, beyond the capabilities of ground-based astronomy. Soon, scientists will be forced to rely on mechanical eyes placed throughout the solar system, orbital telescopes and instruments, to continue tracking and studying this interstellar traveler in its new, altered state. Yet, there is one critical issue inherent to the entire solar system: time. Time that inexorably passes, especially when it comes to such rare and valuable objects as this comet. As it begins to reveal its most intriguing secrets, its rapidly increasing brightness, the inability of ordinary observers to see it in full, and its unusual green glow, all of this happens very quickly. Orbital mechanics, its movement geometry, and its position relative to the Sun and Earth start working against ground-based telescopes, and at the most critical moment of observation, the comet is hidden behind the Sun, making data collection impossible. Even the most advanced professional telescopes equipped with the latest human-made instruments face limitations. As Comet Traitless continues its approach to perihelion, the closest point to the Sun, its position in the starry sky accelerates toward the moment when it will be illuminated and bathed in our star's light with such intensity that its glow will reach an absolute peak. During this critical period, observers encounter numerous difficulties related to the unceasing, intensifying solar light, which hampers clear viewing or detailed recording of this cosmic object. These difficulties are insurmountable even with the most advanced technologies, as no modern equipment can fully compensate for the effects of solar glare and brightness, especially as the comet approaches the Sun. One of the most significant and informative contributions to the study of Triatlas was made by the James Webb Space Telescope. This instrument, capable of obtaining spectroscopic data in the near-infrared range, was able to conduct observations on August 6, when conditions allowed it to safely target its spectrograph at the object. These observations marked a real breakthrough, as they provided crucial information about the chemical composition of the comet during one of the few windows when the telescope's protective systems could shield it from destructive solar radiation. It was during this time that the specific chemical materials present in Triatlas's coma and tail were identified, enabling scientists to make the first detailed conclusions about its nature and composition. These spectroscopic data are among the most comprehensive and accurate ever obtained for interstellar objects of this type, helping to clarify which elements and compounds predominate in this mysterious celestial body. However, these valuable insights were gathered long before significant and dramatic changes in the comet's behavior occurred in mid-September. These transformations turned Triatlas from a relatively unusual and rare object into a truly enigmatic and active phenomenon, raising even more questions and increasing astronomers' interest. In July, the Hubble Space Telescope captured high-resolution images that helped refine the understanding of the structure and dynamics of the jet directed toward the Sun, as well as providing initial estimates of the comet's nucleus size. These images allowed scientists to gain a more accurate picture of the internal structure and activity of the body, as well as its response to approaching the solar star. Unfortunately, after August, the situation changed. New high-resolution images taken with the largest space observatories became much less frequent. The reason for this lies in the fact that objects capable of providing detailed analysis of the comet's behavior proved to be most vulnerable to solar interference and radiation as it neared conjunction with the Sun. As a result, observations that could help unravel the mysteries of Triatlas became very rare and valuable, and acquiring them grew increasingly difficult. It is also important to consider the challenges faced by ground-based astronomical observatories attempting to monitor this object. Different telescopes, employing various filter systems, calibration methods, and data processing procedures, measure the comet's brightness inconsistently. These measurements often do not match each other, which is quite common in astronomy and is related to the peculiarities of instrument operation and atmospheric conditions. Photometry, that is, the measurement of the brightness of astronomical objects, requires careful attention to detail. It is necessary to consider the effects of the atmosphere, weather conditions, light pollution levels, and the accuracy of calibration methods used. All these factors can lead to discrepancies in the results, creating certain difficulties when combining data from various sources. Scientists engaged in collecting and processing observations of comets create databases that accumulate information about the brightness and behavior of objects from around the world. They try to find a balance between different measurements, comparing them with theoretical models to obtain a comprehensive picture. In September, observations conducted with the COPS complex clearly showed that the TRIA. Modern websites involved in tracking space objects gather a multitude of data, which are then processed and transformed into so-called light curves, graphs showing how the brightness of the observed body changes over time. These curves allow scientists to trace the evolution of the object's brightness, identify its activity, and understand the nature of processes occurring within its interior or on its surface. In the case of three atlases observed from different sites, a consistent alarming trend is constantly recorded. The measured brightness values regularly exceed the calculated theoretical trajectories. This deviation is especially noticeable after mid-September, when a clear increase in luminosity is observed. However, the exact magnitude of this deviation remains uncertain, as measurements of such faint and rapidly changing objects are accompanied by significant difficulties and errors. All of this is related to the peculiarities of observing small celestial bodies, whose brightness is at the limit of modern instruments' capabilities, and their rapid changes complicate obtaining accurate data. One of the key factors limiting the quality and duration of observations is solar elongation, the angular distance between the observed object and the Sun, as seen from Earth's surface. This is a crucial geometric parameter that directly affects visibility and data quality. When elongation drops below 30 degrees, even the most powerful telescopes face serious difficulties. Under these conditions, the faint light of the comet is almost lost amid the bright scattered sunlight penetrating through Earth's atmosphere. Professional astronomical observatories typically cease observations when elongation falls below 20 degrees, as the likelihood of obtaining useful data becomes very low. Amateur observers, whose equipment is often less sensitive and more affected by environmental conditions, may lose sight of the object even earlier, facing limitations of their devices and local weather. As a result, the chronology of elongation changes becomes a kind of countdown that cannot be extended by human technologies. The closer the object gets to the Sun, the harder it is to see and record it. By early October, the elongation of the three atlases drops below 30 degrees, marking the beginning of serious difficulties for continued observations. By mid-October, this value decreases to less than 20 degrees, practically ending the possibility of regular observations from Earth's surface. During this period, the object becomes almost invisible to traditional observation methods, and these conditions persist until early November. These weeks are particularly crucial, as this is when solar heating reaches its peak, causing intensified changes in the atmosphere and active processes on the comet. Ironically, precisely at this critical moment, when observing becomes especially difficult, scientists would like to gather maximum data on the object's internal activity. Despite advances in astronomical technologies, such as adaptive optics systems capable of compensating for atmospheric turbulence or coronagraphs designed to block out bright stellar light, they are unable to overcome fundamental physical limitations. When the comet is too close to the Sun in the sky, scattered sunlight passing through the atmosphere creates an insurmountable background, making it difficult or impossible to detect faint signal bursts. In such cases, even the most advanced ground-based instruments cannot provide precise data. As for space observatories like the famous Hubble or James Webb, they have obvious advantages over ground-based telescopes. Positioned outside the atmosphere, they significantly reduce atmospheric interference and allow for clearer images. However, there are also limitations here. These spacecraft are equipped with protective systems that automatically block observations near the solar disk, a necessary measure to preserve their expensive equipment. When solar angles become dangerous, safety systems shut down to prevent damage to the telescopes. Unfortunately, this creates gaps in observations precisely when they would be most valuable for understanding comet activity. The period when the three atlases are in conjunction with the Sun turned out to be the most critical. Processing astronomical data is a complex, multi-stage process that becomes significantly more complicated when observing objects on the edge of visibility. This is especially true for images obtained with the instrument known as the 3-eye atlas, designed for studying comets. These images require meticulous and precise processing to extract the faint signal of the comet itself from numerous interfering factors. The background composed of stars, cosmic rays, as well as artifacts resulting from equipment operation. The closer the comet approaches the Sun, the brighter and more complex it becomes to distinguish its true signal from the bright sky and background. During such moments, data processing stages become particularly important and demand high accuracy, since even minor errors or mistakes in noise removal can lead to distorted results or the appearance of unwanted artifacts that hinder correct interpretation of the observed phenomena. Spectroscopic studies, which are necessary for a deeper understanding of the comet's chemical composition and the structure of its tail, impose more stringent requirements on observation conditions than simple brightness measurements. Instruments designed for spectroscopy work best with bright light sources and when observations are conducted on moonless nights, when the sky is at its darkest. It is precisely during these times that optimal data quality is achieved. However, when the comet disappears into solar glare or its brightness becomes too faint, the opportunities for high-precision spectroscopy are significantly reduced. This is especially relevant when the comet reaches the peak of its activity, and chemical processes within its atmosphere and tail can change very rapidly, requiring timely and accurate analysis. Additional complexity arises from atmospheric conditions, which affect different wavelengths of light unevenly. For example, ultraviolet radiation, crucial for detecting many molecules and substances in cometary atmospheres, is particularly difficult to observe when the comet is in certain positions relative to Earth. Our planet's atmosphere is much more effective at scattering short wavelengths, blue and ultraviolet, than longer ones, red or infrared. This effect, which gives the sky its blue hue, simultaneously creates additional challenges for astronomers aiming to study the chemical processes occurring in the expanding atmosphere of the comet. In such conditions, coordination between different observatories around the world is especially important, as only joint efforts can overcome the limitations imposed by atmospheric factors. Observatories located at various latitudes and time zones must work closely together to maximize the efficiency of the short observation windows available each night. In the southern hemisphere, thanks to geographical features, observation stations can maintain favorable observation geometries slightly longer than their northern counterparts. This creates unique opportunities for extended monitoring of the comet, which is especially important in the case of rare objects like 3I Atlas, as it makes only one pass through the inner solar system. During this single opportunity, it is crucial to record all parameters as accurately and comprehensively as possible. Photometric brightness measurements conducted during observations reflect not only instrumental limitations but also the intrinsic variability of the object itself. Comets can rapidly change their brightness due to gas outbursts, effects caused by rotation, as well as structural changes within the nucleus. Therefore, distinguishing between measurement errors and genuine changes in the comet's parameters becomes increasingly challenging, especially as it approaches conjunction with the Sun, when the signal-to-noise ratio significantly deteriorates. Added to this are weather conditions, which introduce another layer of uncertainty into ground-based observations. Cloud cover, atmospheric turbulence, seasonal climate variations, all significantly impact the ability to perform quality measurements on specific nights. Often, such periods make observations impossible, and missed opportunities may be irretrievable, as there may be no second chances. Unlike periodic comets that return on predictable orbits, the trend observed in the comet's brightness indicators suggests that the value of the parameter designated as 3IATLS consistently exceeds all predicted estimates. Such a jump could indicate several possible causes: active gas emission from within the comet, structural changes occurring in its composition, or simply the presence of systematic errors embedded in the theoretical models used for comparison with actual data. Determining the true causes of this phenomenon and understanding its nature can only be achieved through long-term and highly detailed monitoring, which, however, is often impossible when the comet disappears from view, hiding behind solar glare or bright rays of the sun. When ground-based astronomical observatories reach the limits of their capabilities in tracking the comet, responsibility for continuous monitoring and data collection on its long-term behavior increasingly falls to automated systems and mechanical eyes, telescopes and sensors installed at various points in the solar system. As a result, spacecraft orbiting Mars, designed for entirely different exploratory missions, unexpectedly become key observers of one of the most notable astronomical events of the decade. In this context, a so-called seventh part emerges, dedicated to the growing concern among astronomers and researchers. Despite the restrained and strictly scientific language prevalent in publications, articles, and bulletins, a growing sense of anticipation is emerging within the scientific community. This feeling is linked to the fact that the behavior of Comet Tri-Atlas does not fit within the framework of conventional understanding based on years of research into similar objects. Astronomers are beginning to cautiously acknowledge that they may be witnessing a phenomenon that defies existing theories and models. The trend of brightness variation, observed by both professional and amateur astronomers worldwide, raises concerns that intensify with each new measurement. The fact remains that the comet's brightness parameters continually exceed predictions made by standard models of such objects' behavior. Deviations surpassing expected values by several magnitudes are significantly greater than the typical measurement errors or observational limitations. In recent weeks, Matthew Knight, a comet specialist who has dedicated his scientific career to studying their behavior, noted in a recent interview that the sharp increase in brightness recorded in mid-September casts serious doubt on the reliability and completeness of current theoretical assumptions regarding the mechanisms of volatile and gas release from within the comet. According to him, the rapid pace of these processes indicates the presence of mechanisms operating on timescales much shorter than those usually used to model comet behavior based on gradual surface heating. This uncertainty in scientific forecasts evokes a particular sense of anxiety among researchers and an awareness that phenomena may be unfolding before them, requiring the development of new, more complex theoretical models and hypotheses for full understanding. The reports prepared by Earth-Sky reflect this internal tension caused by ongoing observations, which continue to surprise and challenge existing notions. These materials acknowledge that much of the unusual behavior of the comet could be related to its origin and nature, formed in different stellar systems, making the study of its features especially complex and mysterious. A special focus is placed on the structure of the field cloud directed toward the Sun, which generates its own series of enigmas and questions for scientists. This cloud, as if an expression of new mysteries of nature, stimulates the development of hypotheses and theories that often go beyond conventional ideas about the behavior of such objects. Overall, the situation surrounding Comet Tri-Atlas remains one of the most exciting and simultaneously concerning aspects of modern astronomy, demanding further detailed investigation. Phenomena related to anti-tail structures in comets are well known in comet science and dynamics. However, the consistency and degree of prominence of the leading jets observed in a particular comet sometimes go beyond the usual explanations offered by existing models. In scientific circles, there are frequent attempts to explain such unusual manifestations through increasingly exotic scenarios, including unusual compositions of field particles, extraordinary nucleus rotation mechanisms, or rare mixtures of volatile substances. These hypotheses aim to account for behaviors that contradict standard educational models and traditional notions. Nevertheless, one of the key agreements among specialists studying comets is that the object designated as 3IATL exhibits a level of activity significantly exceeding the typical indicators of ordinary comets at similar distances from the Sun. The distinctive feature of this comet is its coma, primarily composed of carbon dioxide, which has been detected extending into space over unprecedented distances. Such a phenomenon suggests gas emission velocities that substantially surpass standard predictions based on classical models. This is not merely a minor deviation from theoretical expectations but rather a significant and dramatic change that demands a re-evaluation of existing assumptions. At the same time, the scientific community faces a phenomenon known as burst bias, a short-term period of heightened comet activity capable of creating false impressions of its persistent and unusual properties. It is well known that comets tend to experience sudden brightness surges, often followed by an equally rapid return to expected activity levels. Against this background, an important and intriguing question arises. Is the observed increase in brightness of 3IATL in September a genuine deviation from the norm, or is it merely a temporary spike, after which the comet will revert to its usual characteristics? This question is particularly relevant because the uncertainty in its answer is compounded by the prospect of an upcoming observational gap. The most critical period for understanding the true nature of this object is considered to be the week during which the comet passes near perihelion, that is, the closest point of its orbit to the Sun. It is precisely at this moment that solar radiation reaches its maximum intensity, and the comet may undergo the most dramatic transformations. Unfortunately, it is during this period that most observations, especially from ground-based telescopes, are hindered or completely impossible, significantly complicating efforts to understand its current behavior. If the comet indeed experiences its most intense changes during this critical interval, there is a risk that scientists may never fully comprehend what exactly transpired with it in September. For a researcher studying interstellar objects, and especially for Dr. Carrie Holt, who analyzes such objects at the European Southern Observatory, a situation like this is frustrating. She noted that the most critical moment when 3IATL could reveal its main secrets coincides with a period when ground-based astronomy becomes least capable of observing it. She described this temporal conflict as a cosmic conspiracy against scientific knowledge, since it is precisely at this time that observations are most limited and hindered. Debates about the nature of this object go beyond simple questions about its brightness and observable characteristics. They touch on more fundamental issues regarding its physical nature and chemical composition. Spectroscopic studies have revealed that the ratio of carbon dioxide to water vapor in its coma differs from the typical values observed in comets within our solar system. Such a difference could indicate special conditions under which this object formed, possibly in environments significantly different from those characteristic of our local surroundings. Alternatively, it could point to chemical processing that occurred over millions of years of interstellar travel, subjecting it to substantial changes and transformations. Today, amateur astronomical communities play an increasingly important role in monitoring the so-called Third Astronomical Telegram, or, according to international terminology, the Third Asteroid Telescope System, abbreviated as TRI-ATS. These communities, composed of passionate amateurs who approach celestial observations professionally, provide vital support for continuous monitoring of the dynamic processes occurring with bodies such as comets and asteroids. The reason for this is that professional astronomical observatories often cannot ensure round-the-clock, comprehensive tracking of all changes happening in these objects, due to limitations in resources, schedules, and funding. As a result, amateur groups, using their own equipment, often supplement and expand the observation network, enabling the collection of important data in real time and allowing rapid responses to sudden changes in the behavior of observed objects. However, despite the obvious value of this contribution, the fragmented nature of amateur measurements presents its own challenges. Each observer typically uses different equipment, from simple telescopes with digital cameras to more sophisticated systems with specialized spectrometers. Additionally, the data processing methods employed often differ, leading to significant discrepancies in the results of brightness measurements or other characteristics of the objects. Sometimes, the measurements obtained by different observers vary so significantly that the question arises: are these variations a manifestation of real changes in the object, or are they artifacts caused by the peculiarities of the methods or equipment? As a result, determining the true behavior of a comet or other celestial body becomes much more challenging, since many factors influencing the accuracy and comparability of data must be taken into account. Within the framework of international efforts to track and study potentially hazardous or simply interesting interstellar objects, the European Space Agency, ESA, is taking active measures. As part of its Space Situational Awareness Program, which aims to maintain awareness of space conditions, it endeavors to harmonize and coordinate the diverse measurements obtained by various participants. This process involves the use of modern analysis, calibration, and standardization methods, helping to reduce discrepancies between the results of different observers. The primary goal of these efforts is to maintain continuous and comprehensive monitoring of the trajectories of moving celestial bodies and to assess their brightness, which is crucial for understanding their evolution and potential threat to Earth. Analysis of the collected data confirms a general trend of gradual brightness increase in the comet, providing an important clue to understanding its behavior. However, despite this, scientists acknowledge certain difficulties in attempting to quantitatively evaluate the extent of this increase and compare it with theoretical models. In particular, they note that accurately determining how much the brightness exceeds predictions based on modeling or previous observations remains a complex task. This challenge is not only related to measurement accuracy but also to the unpredictability of processes occurring inside the comet, as well as external factors that may influence brightness indicators. Communication and information exchange within the astronomical community are actively conducted through social media, reflecting a mixture of scientific excitement and professional caution. Researchers share preliminary images and brightness measurements, also noting potential uncertainties and limitations in the data obtained. This approach demonstrates that scientists perceive the event as potentially significant, capable of shedding light on new aspects of interstellar object behavior. At the same time, they maintain professional skepticism, avoiding hasty conclusions and emphasizing the need for careful analysis and confirmation of any hypotheses. A particular point of interest is the change in the comet's color, recorded around mid-September. Notably, a green glow was observed, adding another layer to the understanding of the ongoing processes. Scientific hypotheses suggest that such coloration may be related to diatom carbon emissions or other chemicals. In anticipation of a major astronomical event, the approach of the interstellar object known as 3IATL, modern telescopes located around the world are operating in a coordinated manner to maximize observational coverage. The most significant facilities involved are situated in Chile, Navajo, the Canary Islands, and Australia. They synchronize their efforts to gather as much data as possible, especially as the object approaches the period of solar conjunction, which makes ground-based observations increasingly difficult. Each of these unique installations contributes in its own way. Some provide high-resolution images that reveal details inaccessible to others, while some utilize specialized spectroscopic instruments to analyze the composition and properties of the object. Thus, astronomers are making continuous efforts to extract the maximum scientific value from the remaining observational opportunities, despite the impending limitations. Within the professional astronomical community, there are also challenges related to communicating with the public, particularly regarding public statements about 3IATL. Media outlets sometimes tend to overstate the confidence level in scientific conclusions or sensationalize aspects of the comet's behavior that researchers themselves acknowledge as uncertain or insufficiently studied. Balancing public interest in such an extraordinary interstellar visitor with the need to honestly present current research limitations requires careful attention. Proper interpretation and presentation of results become crucial, as any misrepresented or exaggerated information could lead to misunderstandings or even panic. In this context, risk assessment models developed to evaluate threats from hazardous asteroids are beginning to attract renewed attention in the study of 3IATL. Not because the comet poses an immediate danger to Earth, rather, because its unpredictable behavior highlights existing limitations in our current understanding of how small bodies heated by the sun behave. When researchers encounter the inability to accurately predict how this interstellar object will behave in the coming days, important questions arise about the reliability of the models and methods used to assess risks from other small bodies, such as asteroids or comets. The excitement surrounding the 3IATL event reflects one of the fundamental aspects of scientific inquiry: the recognition that nature constantly produces phenomena that are often far more complex and astonishing than human theories and models can anticipate. As October approaches and ground-based observations become more challenging due to solar conjunction, astronomers hope that space probes placed in orbits within the solar system will be able to record discoveries that Earth-based telescopes might miss or be unable to examine in detail under these conditions. In this regard, the ability to obtain unique data from interplanetary satellites and probes becomes particularly important, as they can observe objects in hard-to-reach conditions or during periods when ground-based facilities are not operational. Let's move on to the next significant event, the flyby of Mars, which can be considered a golden opportunity for astronomy. At the moment when Earth is about to lose the chance to observe the 3ITLs due to solar interference, another equally important participant, Mars, will occupy a unique position to observe one of the most significant astronomical events of recent times. On October 30, 2025, Mars will host the closest encounter between humanity and this interstellar object, providing orbiting spacecraft around the red planet with unprecedented opportunities for observation. Unlike Earth-based telescopes, which will be limited by solar conjunction at that time, satellites orbiting Mars will be able to direct their instruments straight at the object passing through our system. Today, international and interplanetary missions launched into Mars orbit continue to perform their tasks well beyond their planned durations, demonstrating the high reliability and effectiveness of the technologies used in space exploration. Among these is the European Mars Orbiter, Mars Express, launched in 2003. This spacecraft not only remains operational to this day but also carries out important scientific missions, exceeding initial expectations for its service life. Its onboard system includes the high-resolution camera HRSC, which over more than 20 years has captured images of the Martian surface with unprecedented detail. Originally designed to study the geological features of the Martian terrain, its sensitivity and resolution now also allow it to be used for more complex tasks, such as obtaining detailed images of the internal structure and core of Comet Third Atlas. Dr. Colin Wilson, the project leader of the ExoMars Trace Gas Orbiter, confirmed that the specialists responsible for mission planning are considering the possibility of utilizing both the color and stereoscopic surface mapping system, known as CAS, and the NOMAD spectrometer, intended for observations of atmospheric layers and the surface of Mars, as well as for studying interstellar objects such as Comet Third ATL. These instruments are capable of analyzing the chemical composition of the atmosphere and surface of the planet, and it is believed that they can successfully detect chemical signatures emanating from an expanding comet, especially in its coma, which consists of gas and dust. It is quite possible that these tools will provide unique data about the comet's composition and the internal structure of its nucleus. Particular attention is given to the possibility of obtaining detailed images with the NASA HiRACE spacecraft, designed specifically for high-resolution imaging. This spacecraft regularly captures the tiniest surface details of Mars, measuring less than 1 meter, from an orbital altitude of approximately 300 kilometers. Although the Comet Atlas will pass much farther from Mars' orbit, the resolution of this camera may still be high enough to observe structural features of the comet's nucleus that remain invisible to ground-based telescopes or less precise satellite systems. Additional opportunities for studying the comet are provided by the spacecraft involved in the MAVEN mission. This NASA program focuses on studying Mars's atmosphere and the volatile substances present within it. It is equipped with spectrographic instruments specifically developed for analyzing the atmospheric composition and the dynamic processes occurring on the planet. Despite their focus on Mars, these instruments could also be very useful for observing the comet Tri-ATL, as it emits gases rich in carbon dioxide, which produce characteristic spectroscopic signatures. However, using such systems to observe a rapidly moving object in interstellar space presents serious technical challenges. The main difficulty lies in the weak signal reaching the onboard instruments. Even at the closest approach to Mars, the brightness of Comet Atlas will be less than ideal. Its visual magnitude is estimated to be around 12 to 14, which is significantly above the detection threshold of most cameras and spectrometers designed for observing large planets. When the comet is at a greater distance, its faint brightness and weak signal complicate the task of obtaining high-quality images and data. Therefore, despite technological advances, observing such objects remains a complex task requiring special solutions and methods. In recent statements, Wilson openly acknowledged the existing limitations related to the possibility of observing Comet Tri-Atlas from an orbital station on Mars. He emphasized that although, in theory, such a task is feasible, the practical effectiveness and scientific value of such observations largely depend on a number of factors. Among them, the brightness of the comet at its closest approach to Mars, the atmospheric conditions prevailing on the surface of the red planet, as well as specific geometric parameters necessary for successful instrument targeting and obtaining high-quality data, are of particular importance. These factors can significantly influence the quality and informativeness of the images and spectra obtained. It is important to note that the advantages of conducting observations from a Martian orbital platform go far beyond simply approaching the object of study. In particular, the geometric configuration during the comet's flyby on October 3 provides a unique opportunity to observe three atlases from Mars, which is not possible from Earth. During this period, the solar phase angles, that is, the angle between the Sun, the comet, and the observer, will differ substantially from the similar parameters observed from the surface of our planet. This difference in perspective angles opens additional opportunities for studying the structure of the comet, especially parts such as its tail, which are hidden from ground-based telescopes due to observational geometry limitations. Thanks to these conditions, scientists will be able to gain new insights into the internal structure of the comet, as well as its tail and its features, which were previously inaccessible. In addition, the interaction of the comet with the solar wind, a stream of charged particles emanating from the Sun, represents another important area where Martian orbiters can play a key role. Such spacecraft equipped with specialized instruments for measuring plasma and magnetic fields can serve as observational platforms for studying the interaction between the comet and the solar wind. The encounter of the comet with this stream may lead to various phenomena, such as disturbances in the magnetosphere or changes in the comet's electrical properties, providing a unique opportunity to gather data on its internal structure and composition. These interactions can not only confirm existing models but also reveal new aspects of the comet's behavior in space conditions. Coordination among various scientific organizations, including the European Space Agency, becomes especially important when organizing observations of the three atlases comet flyby from Mars. This large-scale project involves combining resources and capabilities from multiple space missions, each with its own unique objectives. For example, the Mars Express spacecraft was initially designed to study the geological structure of Mars' surface and its atmosphere. In preparation for the observational phase, it can be used as an observatory for tracking interstellar objects and comets. Similarly, the Trace Gas Orbiter, created to detect methane and analyze the chemical composition of the atmosphere, will need to adapt its instruments for spectroscopic studies of the comet. However, implementing such a large-scale project faces certain time constraints. The time allocated for scientific observations is strictly regulated, as the orbits of the Martian spacecraft and Earth, along with their communication schedules and maintenance routines, are precisely planned. Incorporating observations of the Tri-Atlas comet into these schedules requires careful coordination to avoid conflicts with already scheduled activities and to ensure maximum scientific efficiency. One significant challenge in conducting such observations is the limited bandwidth of radio communication between the Martian spacecraft and Earth. Typically, orbiting stations on Mars can communicate with our space centers only during specific time windows when the planetary geometry allows for the most efficient data transmission. During these periods, the volume of information received from the spacecraft is often limited, and transmitting images and spectra becomes a competing data flow alongside other tasks. Therefore, observations of the Tri-Atlas comet, despite their importance, may cause delays in publishing the obtained results, sometimes by several weeks or even months. This lag is due to the need for further processing, verification, and transmission of data, as well as the limited communication capacity. Today, to effectively study interstellar objects such as comets or asteroids, it is crucial that various scientific and technical organizations around the world work in close coordination. The European Space Operations Center in Germany, the Reaction Control Laboratory of NASA in California, and numerous other specialized facilities and institutions must combine their efforts to plan sequential observations. These efforts include not only selecting optimal moments for observation but also processing vast amounts of data from various instruments and subsequently disseminating the results within the international scientific community. Such a coordinated approach is especially important when aiming to obtain the most valuable scientific information from Mars or other planets, as these successful observations can be decisive in understanding the characteristics of interstellar bodies like 3IATL. The high resolution of the images captured allows for determining the size and shape of the comet's nucleus with unprecedented accuracy, helping to resolve disputes and misunderstandings related to its physical properties and internal structure. Spectroscopic studies conducted by spacecraft can identify molecular species invisible to ground-based telescopes, revealing the chemical composition of the object. This data provides crucial information about its chemical makeup, which in turn holds the key to understanding the conditions under which the comet was formed. A detailed analysis of the core structure, as well as the peculiar tail features, especially the unusual stream directed toward the Sun, this enigma that has baffled scientists, may become clearer when viewed from the unique orbital vantage point of Mars. Different angles of solar illumination allow us to determine whether the structure called the anti-tail is the result of an actual ejection of material toward the Sun or simply a projection effect that manifests differently from various perspectives. It is important to remember that the reality is this: expectations regarding the capabilities of Martian orbital spacecraft must be managed. Even under the most favorable conditions, the scientific results of these observations are likely to include not comprehensive images but only a few spectra and snapshots, because instruments designed for space missions have never been intended for such observations before. Their technical capabilities may be limited, and this may not be enough to provide definitive answers to fundamental questions about the nature and behavior of the interstellar object 3IATL. The success of such observations largely depends on variables beyond human control. For example, if comet 3IATL manages to survive another increase in brightness, expected around October 3, it could become bright enough for instruments on Martian orbiters to detect, whereas otherwise, it will remain too faint for registration. Conversely, if the comet begins to fade and loses its current brightness level, even the most optimistic observation scenarios may not yield the desired results. In this context, the flyby of Mars presents a unique opportunity for humanity to continue tracking 3IATL during the weeks when ground-based telescopes lose sight of it. Since terrestrial astronomy will have to remain silent for some time, awaiting the start of November, it is the orbiting spacecraft around Mars that serve as the only reliable platform for observing this interstellar traveler. These observations could become the most dramatic phase of 3IATL's encounter with our solar system, as they offer a chance to record its behavior under conditions as close to reality as possible. Regardless of whether comprehensive data can be obtained or not, such missions mark a new era in the study of interstellar visitors, demonstrating our ability to coordinate efforts on an international level and utilize multiple planetary platforms simultaneously to gather information. This is a testament to the growth of humanity's technological and scientific potential, for even objects traveling at interstellar speeds become part of a collective observation system, united by a common goal: to understand them. As October approaches and the three atlases steadily draw closer to the Sun, a moment arrives when the geometric patterns of orbital motion begin to play a special role. It is during this period that they start to speak the language of celestial figures, foreshadowing that our interstellar visitor may reveal its deepest secrets only when its position relative to the Sun reaches a certain point. This period, which astronomers call the superior conjunction, is precisely when the three atlases are at their closest to the Sun, creating unique conditions for observation. On clear nights, when the sky is perfectly transparent, this event transforms one of the most significant astronomical moments in recent history into something extraordinary and memorable. At this time, a so-called cosmic act of disappearance occurs, when the object seems to dissolve into the boundless darkness, vanishing from the observer's field of view. The chronology of this process develops with astonishing precision, as if measured by clockwork, leaving no doubt about its strictness. In early October, as the Sun rises higher above the horizon, the three atlases dip below the 30-degree mark of solar elongation, which is a critical threshold for ground-based telescopes. It is at this moment that serious difficulties begin for astronomers, as Earth's atmosphere becomes increasingly obstructive. The scattering of sunlight creates a bright sky background that drowns out faint signals from the interstellar visitor, rendering it virtually invisible to observers. Even professional observatories equipped with highly advanced adaptive optics and high light gathering power can only slightly extend the observation window. However, they also face mounting obstacles. By mid-October, the the angle between the line of sight from Earth to the object and the line connecting it to the Sun shrinks to less than 20 degrees, making regular observations nearly impossible. At that point, all observation turns more into a guessing game than into genuine study. The comet does not vanish suddenly, as if by magic. It gradually dims, losing its brightness under the sun's rays, much like a star at dawn when pre-dawn darkness slowly gives way to the first light of a new day. This process occurs slowly but inexorably, and each day it becomes more difficult to notice it, until finally, observation becomes entirely impossible. This slow and gradual transition complicates the precise determination of the moment when Earth finally loses visual contact with the three atlases. However, from the perspective of practical astronomy, the outcome remains the same. Our primary window for studying this interstellar object closes precisely when solar heat reaches its maximum intensity. The period of maximum conjunction lasts approximately 4 to 6 weeks, covering the time when the three atlases remain virtually invisible from Earth's surface. This event is not merely an inconvenience or a temporary difficulty for observations. It represents a complete loss of our ability to control and study the comet during the very moments when, according to theories, its activity should be reaching its peak. It is during this period that the gas emission peaks, the tail forms and develops, and potential collisions or even fragmentation of the object may occur. All these dramatic processes often happen covertly, behind a veil of sunlight, remaining beyond human eye reach. Ironically, this becomes especially poignant when recalling recent observations of the object known as 3I Atlas. In September, its brightness significantly increased, attracting heightened attention. The unusual structure of the anti-tail, which surprises specialists, as well as its characteristic green hue, all indicate that the object is undergoing serious, fundamental changes under the influence of solar radiation. All of this points to some transformation occurring within the comet as it encounters intense heat and radiation from our star. Logic suggests that as it approaches perihelion, the point in its orbit closest to the Sun, the physical laws underlying the phenomenon of maximum conjunction do not imply any conspiracy or trick aimed at hiding or distorting scientific discoveries. In reality, these laws are merely consequences of the geometric features of observations, which arise from the relative positions of our planet and the objects orbiting the same star as our solar system's center. When the comet, known as 3 Atlas, approaches perihelion, the point in its orbit nearest to the Sun, its apparent position in the sky inevitably begins to approach the Sun. This is because, as it nears perihelion, the angle between the comet and our star gradually decreases, ultimately aligning the comet almost directly with the Sun, creating unique conditions for observation. This reduction in angular distance continues until the comet passes behind the Sun, the moment when it is positioned behind our star and becomes inaccessible for observation not only from Earth but also from most spacecraft. It is precisely during these periods that all technological means, no matter how advanced and sophisticated, reach their limits. Professional astronomers who study celestial objects regularly face this limitation. No matter how advanced the technology, it cannot penetrate the bright sunlight to observe objects that are in such close proximity to the Sun as a comet during conjunction. Some satellites designed for solar observations, such as the Solar and Heliospheric Observatory, SOHO, occasionally allow for observations of comets during these conjunctions. They use special coronagraphs, devices that block direct sunlight, creating an artificial shadow to enable the observation of surrounding objects. However, the trajectory of Comet 3 Atlas during its conjunction with the Sun is too far from the solar surface to be captured by such instruments. Typically, coronagraphs are tuned to observe objects near the solar corona, within a few solar radii from our star. Consequently, during conjunction, the ability to detect the comet with these devices is significantly reduced. This creates unprecedented challenges for the scientific community, which is accustomed to continuous, uninterrupted observations. In the modern era, astronomy largely relies on long-term observational campaigns aimed at tracking changes in objects over their entire activity cycle. In the case of comets, especially such as 3 Atlas, long-term monitoring is necessary to distinguish short-term outbursts related to gas and dust emissions from more stable changes that reflect their long-term evolution. When, at the most critical moment, during conjunction, a sudden interruption in observations occurs, it precludes the possibility of conducting a comprehensive analysis that considers all nuances and the dynamic behavior of the object. The use of spacecraft within the solar system offers some alternative to ground-based observations. However, the capabilities of such devices remain quite limited, as most are missions designed for studying planets and their moons, not for continuous tracking of comets. For example, spacecraft orbiting Mars can provide some observations in the short term, but their activity is more momentary in nature. They can deliver images or data at specific times but are unable to provide the continuous monitoring necessary for a full understanding of the processes occurring with Comet 3 throughout its approach and recession from the Sun. One potential source of information about the comet is the Bepi-Colombo mission, operated by the European Space Agency, which is currently heading toward Mercury. The trajectory of this spacecraft allows, in certain cases, for random observations of Comet 3 from a perspective different from Earth's. Such observations can provide valuable information, especially considering that the spacecraft's orbit and orientation models used to predict the comet's activity are largely based on data collected during observations of this mysterious interstellar visitor. These observations serve as a necessary foundation for calibrating theoretical calculations and verifying their accuracy. However, when observations cease for approximately 4 to 5 weeks, critical information for modeling disappears, making it more difficult for scientists to understand how this celestial object responds to solar heating. It is during these periods, when ground-based observatories temporarily do not record the comet, that the opportunity to monitor its development and dynamics is lost, significantly complicating astronomers' work. After observations resume, presumably in November or early December, the comet's condition could change dramatically. At that point, the object known as the IAT Atlas may appear quite different from how it was remembered in September. The comet could become brighter, and its tail structures more impressive and visible even through amateur telescopes. At the same time, there is also the possibility that it could fade significantly if, during an unnoticed perihelion passage, that is, when it reaches its closest point to the Sun, all volatile substances are exhausted. A more dramatic scenario involves the potential for the IAT Atlas to completely disintegrate into several parts as it reaches its closest approach to the Sun. Comet disintegration is not uncommon in such situations. Near perihelion, where gravitational and thermal forces peak, a weak comet nucleus often cannot withstand these impacts. Tidal forces and high temperatures can overcome the weak gravitational attraction holding the nucleus together, leading to its destruction. If such a breakup occurs precisely when the comet is near the Sun, it will pose a serious challenge for Earth-based observers. After reappearing in the sky following a period of invisibility, it may present itself as a multitude of separate fragments, each requiring individual observation, identification, and tracking. This will significantly complicate astronomers' efforts, as determining their positions, brightness, and characteristics will be much more difficult. Resuming observations at the end of November or early December will require careful preparation and coordination among observatories worldwide. After the conjunction period, when the comet has disappeared from view, it will emerge from behind the celestial horizon in another part of the sky, demanding even more precise and coordinated efforts from telescopes to locate and reacquire the object. During this time, its brightness, position, and appearance can change so significantly that even experienced astronomers may struggle to recognize and track it. All these nuances require careful attention and meticulous planning to avoid losing the object entirely and to conduct the necessary observations in a timely manner. Public interest in Comet 3 IAT Atlas is undoubtedly linked to its movement and changing visibility. During the period when it shines brightly and attracts attention with its tails and unusual activity, the media actively cover the news, publish vivid photographs, and provide updated information about its condition. Such coverage helps maintain audience interest, creating the impression that this is a genuine space event worthy of attention. However, when the comet disappears behind the Sun's glare, a forced silence ensues. At this moment, the opportunity to gather new observations vanishes, significantly reducing the flow of information and, consequently, public interest. It is especially frustrating that during this period, the comet may experience its most luminous and spectacular changes, development of tails, activation of the nucleus, and possible explosive brightness increases. All of these are crucial moments for visual demonstration and educational purposes, but they remain inaccessible until the object reappears. The lack of data during the conjunction serves as a stark reminder of the fundamental limitations of astronomy. Despite centuries of technological advancements and observational methods, humanity remains connected to its planet. Even the most advanced and complex space telescopes available today cannot fully eliminate all constraints associated with observing objects when they come too close to our star, the Sun. In such moments when a celestial body is at a very close distance, its illumination and brightness become so intense that even the most powerful instruments lose the ability to clearly capture details and expand the scene. As the three IAT atlases, large astronomical tools designed for tracking and studying interstellar objects, fade into the bright solar glare, the astronomical community worldwide prepares for a period filled with uncertainty, speculation, and theoretical models. These models and assumptions are based on incomplete data, obtained with difficulty, and require subsequent confirmation. The question posed within scientific circles is not whether the comet will change during its hidden passage past the Sun. Rather, it concerns whether these changes will be observable and understandable after observations resume, or whether, on the contrary, they will remain mysteries, eternal secrets about what transpired during the most critical moment of its encounter with our star. These mysteries may remain inaccessible to humans, as there can be a significant amount of time and many light years between the active phase and subsequent observations, increasing the risk of losing important details. As for the next critical stage of the comet's encounter with the solar system, preparations are now in full swing, and it is called waiting for perihelion. Deep within the bright sunlight, which is so blinding to telescopes on Earth, preparations are underway for the most important and fateful encounter of this interstellar traveler with our star. According to plans, this unique object, known as the Third Atlas, is expected to reach the point in its journey called perihelion between October 29 and 30, 2025. At this moment, the comet will reach its closest approach to the Sun, passing at a distance of approximately 136 astronomical units, roughly 150 million kilometers or a little over 93 million miles. Such a close pass, often hidden from human view, will expose the comet to intense solar radiation streams, unparalleled during its multi-million-year journey between different star systems. As a result, transformations may occur that could completely change our understanding of interstellar objects, their structure, and behavior. The very change in velocity observed in this comet indicates that it is subjected to cosmic violence, powerful forces acting upon it throughout its long voyage. Currently, as it speeds through space at tens of kilometers per second, this motion is impressive. But by the time it reaches perihelion, its velocity could peak at about 6.8 kilometers per second, which translates to nearly 152,000 miles per hour. To grasp how fast that is, remember that Earth orbits the Sun at about 30 kilometers per second. Compared to this, the comet's speed will be more than twice that of our planet, meaning it possesses enormous kinetic energy accumulated during its epic journey through the galaxy. Physical laws predict that it is precisely at perihelion that the comet will experience the most dramatic and eventful phase of its approach to the Sun. At this point, solar heat will reach its maximum, and the temperature of the comet's nucleus will rise sharply. This could cause the remaining volatile substances inside to actively sublimate, turning into gas and creating a bright expansion of the coma, a cloud of dust and gas around the nucleus. Such an expansion could surpass in size and intensity everything previously observed. Theoretical models based on modern understandings of the composition and behavior of comets suggest that the presence of a significant amount of carbon dioxide in their makeup, referred to in certain models as 3ATLS, may lead to unusual and highly pronounced activity as they pass through perihelion, the point in their orbit closest to the Sun. Specifically, these models indicate that this composition can trigger processes different from those typical of comets known in our solar system. Why does this happen? The key lies in the fact that carbon dioxide present in comet nuclei has the ability to sublimate, transition directly from a solid to a gaseous state, at much lower temperatures than water or ice, which constitute the majority of traditional comets. Near perihelion, temperatures can reach levels at which carbon dioxide begins to actively escape, creating powerful gas outbursts that significantly exceed the velocities typical of water-dominated comets. As a result, the activity of such objects may manifest as rapid changes in their brightness and size, as well as in the structural transformations of their tails, occurring within hours rather than days or weeks, as is usually observed during the gradual evolution of classical comets. This heightened activity is likely accompanied by numerous complex processes, among which nucleus fragmentation holds a special place. This scenario casts a shadow of uncertainty over predictions related to the behavior of comets as they approach perihelion. Overall, comets are considered among the most fragile and vulnerable objects within our solar system, since their structure, mainly composed of ice and dust, is held together only by weak gravitational bonds and the internal integrity of icy matrices. These matrices are typically highly porous and loosely bound, making them especially susceptible to external influences. Under conditions of intense solar heating, which causes significant thermal stresses, and under the forces generated by sudden gas and dust outbursts, internal forces can exceed the cohesion limits, leading to the rupture of the nucleus into parts. Such fragmentation can occur suddenly and with dramatic intensity. A comet that appears quite stable during its approach to perihelion can suddenly disintegrate into several pieces within hours. All of this is driven by thermal gradients created by rapid heating, which generate internal weaknesses in the nucleus's structure or trigger powerful gas eruptions that literally eject material from its interior. Consequently, the internal layers of the nucleus are destroyed, and fragments begin to detach from each other. If such a comet, for example, one composed of 3 ATLS, undergoes fragmentation, observers on Earth will face a significant challenge. They will need to identify and track several objects simultaneously, which may then disperse in different directions and vary in size. Reconstructing their trajectories and predicting their future behavior will become much more difficult, especially when observations resume after a certain period, say, in November. Historical examples of comet fragmentation near perihelion provide clear confirmation of this theory. One of the most well-known cases is comet Shoemaker-Levy 9, which in 1994 broke apart under the tidal forces of Jupiter, even before reaching the planet itself. This example demonstrates how sudden and powerful the destruction process can be. Recently, in 2013, the disintegration of comet Ison occurred during its extremely close approach to the Sun. During this event, a large cloud of debris formed, which quickly dispersed as the comet moved away from perihelion, making the fragments nearly invisible and complicating their tracking. However, it is important to remember that fragmentation is not an inevitable outcome. If the triple object in question successfully survives its closest approach to the Sun, the perihelion, without significant damage or destruction, a completely new era of development and transformation will open for it after this crucial astronomical event. During this period, as the object leaves perihelion, its appearance and internal structure can undergo radical changes due to the intense and bright solar radiation it encounters near the solar orbit. The coma, the expanded and luminous envelope surrounding the comet's nucleus, can significantly increase in size compared to its initial dimensions, as powerful peak gas production velocities cause material to be ejected and spread into space with such force that it creates vast volumes of interstellar space previously unobservable. As a result of this vigorous outgassing and dust release, new chemical species may emerge, substances previously hidden beneath the Earth's crust or inside the nucleus, which, when heated and exposed to solar ultraviolet radiation, could be detected for the first time in astronomical spectroscopy. These new molecules, freed from the depths, might manifest themselves in the spectra, altering the comet's color palette beyond the usual green hues already observed. As different molecular structures begin to fluoresce, emit light under the influence of ultraviolet rays. Observers may see the comet's spectrum change, acquiring new shades and brightness levels. If complex organic compounds are present in the comet's nucleus, then under intense heating and exposure to solar radiation, they can decompose into simpler molecules and fragments. These, in turn, begin to emit light at characteristic wavelengths, creating a rainbow effect, a rich spectrum of emissions covering the entire visible range. These luminous phenomena can become particularly bright and noticeable, allowing scientists to better understand the comet's internal chemistry and physical structure. One of the interesting phenomena characteristic of this period is the so-called anti-tail flow, or anti-tail, which was first observed in the case of a triple object designated as the 3 Atlas. Near perihelion, this phenomenon can undergo significant changes, as increased dust and gas emissions lead to the formation of multiple tail structures pointing in different directions. Each of these structures forms as a result of particles of various sizes reacting to solar radiation pressure, causing their deflection and the formation of complex geometric configurations. Such diverse tail shapes and their orientations can provide valuable information about the rotation speed of the nucleus, the composition of the surface, and the internal structure of the comet. Analyzing the distribution and composition of particles ejected from the nucleus becomes critically important at this stage because it helps to understand the internal conditions and mechanisms behind the formation of the original object. For example, large grains, if found within the dust, may indicate a loosely cemented nucleus with large voids inside, while fine dust suggests a denser structure or the presence of chemical elements that promote the formation of small particles. The magnetic and plasma environment surrounding the object at perihelion also plays a significant role in comet studies. The interaction of the solar wind, a stream of charged particles emanating from the solar corona, with ionized gases in the coma causes complex electromagnetic phenomena. These interactions can accelerate particles to tremendous speeds, resulting in bright glows and light effects within the coma, as well as the formation and development of long plasma tails extending millions of kilometers behind the nucleus. Regarding temperature characteristics, measurements of the comet's temperature during its approach to the Sun, if such data can be obtained through spacecraft or other observational methods, are crucial. Objects moving with large reserves of volatile substances can remain active for extended periods after perihelion, sometimes for several weeks, and in some cases, even months. This prolonged activity is associated with the presence of a significant amount of volatile substances in these objects, which begin to evaporate as they approach the Sun, creating a bright, noticeable comet-like atmosphere and tail. In contrast, objects with a relatively small reserve of volatiles may quickly lose their activity as their surface layers are depleted or burn out under the influence of solar heat. Gravitational perturbations caused by the strong gravitational field of the Sun, especially near perihelion, the point in the orbit closest to our star, play a crucial role in shaping their trajectory and subsequent behavior. These gravitational forces can influence the future path of a comet or other interstellar object, particularly in the context of the outer planets of the solar system, such as Jupiter, which is the largest planet and a powerful gravitational trampoline. Although, in essence, one can consider that the object will continue moving outward along a hyperbolic trajectory. That is, it will permanently leave the system. Small changes in its velocity and direction can significantly affect the timing of its approach to planets or the nature of its future encounters. The closest passage near Jupiter is especially important. Planned 200 years from now, it could become a key event in the object's subsequent behavior. Passing through perihelion is undoubtedly the climax in the history of this interstellar object, as it encounters a powerful radiation environment surrounding our Sun, and its interaction with this intense radiation can lead to a variety of effects. These effects may manifest as spectacular cosmic fireworks, bright flares and outbursts of material, as well as quiet but significant structural changes within the object itself. Inside an expanding comet or another interstellar visitor, perihelion can radically alter its internal composition, structure, and appearance. This moment essentially transforms the object from what it was before encountering our Sun into something new, unique, and unprecedented in its history. The question that will undoubtedly occupy astronomers' minds during the period when the object is in close proximity to the solar perihelion is: will it retain its recognizable shape and properties, or will its encounter with the intense radiation and solar radiation drastically change its external appearance and internal structure? The answer to this question lies in the solar radiation itself, which is literally waiting for this object to approach, and in precise orbital mechanics calculations that will help understand exactly how the influence of perihelion will manifest in its subsequent behavior. Time will tell whether this interstellar traveler, known as the 3 Atlas, will emerge from the zone of intense solar influence as a recognizable and familiar object, or if it will be completely transformed into a new phenomenon in the astronomical world. Now, let us turn to a comparative analysis to understand how unique and significant this object is within the context of interstellar travelers' history. To fully grasp the role and importance of the 3 Atlas and its unusual behavior, it is necessary to look back at a brief yet revolutionary era when the existence of interstellar visitors was first confirmed, and only 2 of them were definitively identified as aliens from beyond our solar system. These 2 objects not only astonished astronomers with their behavior but also forever changed our perceptions of space and its diversity. Each of them, in its own way, rewrote astronomy textbooks, opening new horizons for the study of interstellar travelers. Collectively, these stories tell us something profound. The question arises: was this gas release from hidden volatile deposits, or does the cause lie in something more mysterious and unusual, beyond the scope of conventional physical laws? Perhaps the object was affected by radiation pressure from the Sun acting on its unusual shape, or perhaps some exotic mechanisms, not yet understood by modern science, are at play. The absence of a noticeable comet near Oumuamua, despite expectations for such objects rich in volatile ices typical of comets, remains a true mystery. Nevertheless, something did influence this cosmic object, causing the observed acceleration in its movement. And if we are to consider this explanation as valid, it boils down to the fact that the gas release occurred so subtly and in such small quantities that it remained undetectable by our instruments, yet generated enough force to alter the trajectory of Oumuamua. The second object, named 2I Borisov, was discovered on August 30, 2019, by amateur astronomer Gennady Borisov, working in Crimea. This object presented a completely different profile compared to the first. Unlike the mysterious behavior of its predecessor, Borisov initially appeared to be a typical comet, with a characteristic bright coma and developing tails consistent with our theoretical understanding of such celestial bodies heated by solar radiation. However, a more in-depth and thorough analysis revealed that the apparent external normalcy concealed a chemical composition significantly different from what we are accustomed to seeing in comets originating from our solar system. Spectroscopic observations revealed concentrations of carbon monoxide significantly higher than those typical of local comets, indicating that such bodies formed under conditions in the protoplanetary disk with temperature and chemical gradients far different from those that existed in our own nebula. Additionally, the dust-to-gas ratio in Borisov's coma was different. It suggested either different formation processes or evolutionary changes that occurred during its interstellar journey. These subtle yet highly significant chemical differences first confirmed that comets from other stellar systems can have unique compositions, reflecting their formation conditions, which differ from those characteristic of our region of space. Now, the third interstellar object, designated as 3I Atlas, joins this exclusive club of unique cosmic bodies with features that make even its predecessors seem ordinary. Discovered by space physicists and confirmed through subsequent observations, this comet represents the most extreme deviation from the norms of the solar system, as understood by our current knowledge, ever recorded among interstellar visitors. The ratio of carbon dioxide to water vapor, derived from data collected by the James Webb Space Telescope, indicates formation conditions that were even more unusual and exotic than those that led to Borisov's appearance. The structure of the anti-tail, directed toward the Sun, has no parallels in previous cases of interstellar objects, whereas Oumuamua did not exhibit tails due to the absence of significant gas emissions. Unlike them, Borisov had typical cometary tails pointing away from the Sun, while 3I Atlas creates a geometric configuration that directly contradicts the fundamental laws of physics established over more than a century of comet observations. The acceleration of brightness observed in September 2025 adds another unique and essentially inexplicable characteristic to the growing list of anomalies associated with this interstellar object, raising more questions among scientists and casting serious doubt on existing theories about the nature and behavior of such cosmic visitors. Neither Oumuamua nor Borisov exhibited such abrupt and noticeable changes in brightness over a relatively short period, indicating that 3I Atlas is subject to ongoing, albeit less dramatic, processes. These processes may include gas emissions, structural transformations, or long-term surface evolution occurring over timescales much longer than those observed in other interstellar objects. This conclusion is based on comparative analysis, which reveals patterns in the sizes of these cosmic visitors. For example, the dimensions of Oumuamua, estimated at approximately 40 by 40 by 400 meters, make it noticeably larger than most small asteroids, yet still smaller than the majority of active comet nuclei. At the same time, Borisov's nucleus, which measures about 1 kilometer in diameter, falls within the typical range for comets known in our solar system. The size estimate of 3I Atlas, obtained through data from the Hubble Space Telescope, indicates that its diameter ranges from roughly 3,200 meters to 6 kilometers. Such a broad range encompasses both small and moderately large comet nuclei, reflecting a high degree of uncertainty in determining its exact size. The primary challenge in this regard stems from the difficulty of separating the nucleus from the extensive coma surrounding it, a characteristic that is unique and distinguishes 3I Atlas from other interstellar objects known to date. Modern capabilities for chemical analysis of interstellar bodies have significantly improved since the discovery of each new visitor from interstellar space, enabling more detailed studies of their composition and physical nature. However, for Oumuamua, due to its brief visibility period and lack of noticeable gas emissions, chemical analysis was limited to surface reflection properties and rough density estimates. In contrast, Borisov's situation was different. Its longer stay within the observational field allowed spectroscopic methods to detect molecules such as water vapor, carbon monoxide, and other components characteristic of comets, especially their active nuclei. As a result, new information about the chemical composition of this interstellar object has been obtained through the use of the most advanced observational tools ever applied to interstellar bodies. In particular, infrared spectroscopy conducted with the James Webb Space Telescope, along with high-resolution images from the Hubble telescope and data collected by ground-based observatories equipped with next-generation spectrographs, provide unprecedented insights into the composition, internal structure, and dynamics of these objects. These detailed observations enable tracking their temporal evolution and understanding the processes occurring within their interiors and on their surfaces. Turning to the characteristics of the orbital trajectories of each interstellar visitor, they tell individual stories about the processes occurring in the galaxy and related to the ejection of such objects from their parent systems. For instance, Oumuamua approached the solar system from the direction of Vega. However, its trajectory was significantly longer in duration than the age of Vega itself, indicating a more complex and tangled galactic path. Its hyperbolic velocity, that is, the speed it would maintain after leaving the Sun's gravitational field, was approximately 26 kilometers per second. At the same time, Borisov's trajectory indicates an origin from the region where young, hot stars of the constellation Cassiopeia are located, and its hyperbolic speed approached 32 kilometers per second. The higher velocity of this object suggests either its ejection from a more massive and dynamic stellar system or acceleration due to gravitational interactions during interstellar travel, making its path even more unusual and intriguing for study. The object, designated as the triple star asteroid or simply 3 Atlas, currently holds the record for the highest hyperbolic speed ever observed for an interstellar body. This speed reaches about 49 kilometers per second, which is truly extreme. Such an extraordinary velocity implies that this object either formed in the vicinity of a particularly massive star with significant gravitational pull or was accelerated through numerous gravitational interactions during its journey across the galaxy. The influence of such a speed on the object's behavior and characteristics is especially noticeable near its perihelion, the point in its orbit closest to the Sun. The higher the velocity, the less time the object has to absorb solar heat into its structure and reach its core, significantly affecting its thermal and physical state in these regions. The intervals between the discovery of interstellar visitors such as Oumuamua, Borisov, and the recently identified 3 Atlas provide valuable insights into the scale and characteristics of such bodies in our galaxy. For example, the 2-year gap between the discovery of Oumuamua and Borisov, followed by a 6-year interval before the detection of 3 Atlas, indicates that similar objects repeatedly pass through the inner regions of the solar system. However, their detection remains a challenging task due to their small sizes and brief visibility periods from Earth. These factors make them rare and difficult to find, despite their regular passage through our region of space. A statistical analysis of the 3 confirmed interstellar objects shows that each one results from different formation processes of small bodies in other star systems. This suggests that the galaxy as a whole produces and ejects comets and asteroids through a variety of scenarios, differing in structure, chemical composition, and formation mechanics. As a result, each new interstellar visitor broadens our understanding of the possible range of such bodies' characteristics, demonstrating that their properties do not conform to a single pattern or standard models. The unique features of the 3 Atlas are particularly striking: its extraordinary size, the structure of its anti-tail, chemical composition, and brightness variation dynamics. All of these indicate that the diversity of interstellar objects includes phenomena and properties that have yet to be predicted or even imagined by theoretical models based on our solar system studies. Each such interstellar passage teaches astronomers important lessons about planetary formation processes occurring throughout the galaxy. At the same time, these objects raise new questions about what other types of interstellar bodies await discovery and what role they play in cosmic evolution. While the 3 Atlas continues its covert journey through the perigee region, scientists can only speculate whether its appearance after passage will add new entries to the growing catalog of interstellar object features. A model based on observations of Oumuamua and Borisov suggests that the 3 Atlas will continue to surprise researchers with its behavior, casting further doubt on existing notions of the fundamental physical laws governing small bodies. Studying such objects demonstrates that the galaxy forms small bodies through processes far more complex and diverse than those occurring in our solar system. Each object carries unique traces of its chemical and physical origins, sharply distinguishing it from known cosmic bodies and providing a direct means to investigate the conditions of planetary system formation at various stages of their evolution across the Milky Way. Part 12 of this scientific study is dedicated to the numerous uncertainties and active debates within the scientific community. The scientists' reaction to the discovery of the 3 Atlas resembles a tense detective story, where decisive clues are either locked away behind sealed doors or remain elusive. Currently, there are many hypotheses and theories, each attempting to explain the comet's unusual behavior, yet all raise new questions and doubts. However, none of the existing assumptions are comprehensive enough to fully reveal all the nuances of its nature. In most cases, we can only say that a final understanding will be possible only after new observations are obtained, those made after the celestial object's conjunction with Earth, that can fill in the missing pieces of this complex interstellar puzzle. One of the challenging issues is the contradiction in determining the size and shape of the comet's nucleus, vividly illustrating the fundamental problems faced by modern researchers studying this object. For example, data obtained from the Hubble Space Telescope have narrowed the estimated diameter of the nucleus to approximately 3/12 of a kilometer and up to about 6 kilometers. Nevertheless, even this relatively narrow range demonstrates significant uncertainty, as it is extremely difficult to determine the precise boundary between the solid core and its surrounding coma. This uncertainty is important not only because it affects the accuracy of the object's size measurement but also because the size directly determines the comet's mass, its density, the surface area available for gas emission, and its structural stability during periods of intense heating, especially at perihelion, the closest point to the Sun. Different measurement methods often yield conflicting results. For example, thermal modeling based on infrared observations suggests the presence of a smaller core with a high albedo, meaning it reflects sunlight efficiently, indicating a light-colored surface. At the same time, analysis of visible spectra indicates a larger, darker core that absorbs more solar radiation, implying a more massive and darker surface. These discrepancies may be caused by differences in the surface composition of the comet, measurement errors, or perhaps deeper misunderstandings of how the object responds to solar heating and how its composition influences reflection and absorption properties. The analysis of the comet's chemical composition also faces several contradictions. Spectroscopic studies conducted by the James Webb Space Telescope have clearly identified carbon dioxide as the dominant volatile component in its coma, making up about 3% of its volume. Meanwhile, the carbon dioxide concentrations significantly exceed those of water vapor, which sharply contrasts with the composition of comets within our solar system, where water vapor is usually the predominant volatile substance. This dominance of carbon dioxide presents theoretical challenges when attempting to explain other observed parameters of the comet. For instance, in September of this year, a green glow was observed on the comet's surface, typically associated with the emission of diatomic carbon. However, the release of carbon dioxide-rich gas does not directly lead to the formation of molecules responsible for the green emission, raising questions about the causes of this phenomenon. It is possible that spectroscopic studies have overlooked important chemical components, or that the green coloration results from processes far more complex and multi-stage than simple molecular emission. Additional investigations using ground-based observatories and large telescopes have revealed the presence of various complex molecules in the comet's coma, such as cyanide compounds and organic substances. These discoveries indicate a rich chemical composition and suggest that the comet's chemical nature is far more intricate than previously assumed. As a result, it becomes evident that the comet contains not only simple carbon-based compounds such as CO2 but also more complex organic molecules, indicating a rich and diverse chemical history for this object. The structure of the anti-tail appears particularly complex and mysterious, an elongated and unusual formation that often sparks debate among researchers. Traditional comet physics states that the pressure of solar radiation causes material to be ejected primarily in the direction opposite the Sun, meaning away from it. However, observations of this object suggest that the structure forming the so-called anti-tail is likely governed by different laws. Recently, an innovative theoretical study has emerged within the scientific community, conducted by Dr. Kett and Dr. Loeb. Although it is currently undergoing peer review and has not yet been published, it has already garnered significant interest. The study proposes a hypothesis that the anti-tail is formed due to an unusual distribution of dust particle sizes, as well as a unique geometry of material ejection from the comet's nucleus surface. Their model suggests that large dust particles, ejected toward the Sun at sufficiently high initial velocities, can overcome the pressure of solar radiation and, moving forward, create observable structures oriented precisely toward the Sun. As a result, the structure formed by these large particles appears as a convex formation directed forward, i.e., toward the Sun, opposite to the typical tail. However, it is worth noting that there are several alternative models based on different physical mechanisms. Some scientists propose that electromagnetic effects, arising from interactions between charged particles and solar magnetic fields, can redirect the flow of material into unexpected directions, not aligning with simple radiation pressure models. Others believe that the rotation state of the comet, in this case, the so-called triple atlas, creates thermal asymmetries on the surface, which in turn promote the concentration of gas emissions in specific directions, regardless of solar radiation pressure. Determining the precise rotational characteristics of this comet is challenging. Over many months of observation, scientists have been unable to detect clear signs of periodic rotation. Analysis of the brightness curves, which measure changes in the comet's luminosity caused by its rotation and the uneven distribution of active zones on its surface, has also failed to reveal distinct or repeating signals. The absence of obvious periodic oscillations may indicate that the comet rotates very slowly or that its shape is nearly spherical, which significantly complicates the detection of regular signs of rotation. It is also possible that the rotation is too complex and tangled, hiding simple, easily recognizable cycles. Nevertheless, the rotational state of the comet is one of the key factors influencing its behavior and development. Fast-rotating objects, due to centrifugal forces, experience additional stresses on their structure, which can, in turn, affect gas emission models and the overall stability of the comet's structure. Conversely, slowly rotating bodies develop temperature gradients between their day and night sides, promoting the concentration of volatile substances in heated areas and impacting activity. Unknown parameters of the rotation of the Triple Atlas greatly complicate attempts to model its thermal evolution and make accurate predictions about the future behavior of this unusual celestial object. Throughout September, observational networks around the world recorded significant changes in the brightness of this cometary body. According to documented data, the comet's brightness increased substantially, by more than a few magnitudes, certainly sparking lively interest among astronomers. However, the extent of this deviation from theoretical predictions is subject to debate. Some experts believe that the brightness increase was so noticeable that it can be compared to several magnitudes, meaning a significant and obvious rise in emission intensity. Others argue that these changes could be much more modest and fall within the range of typical variability observed in most comets. One reason for such disagreements is the difficulty in obtaining precise measurements. Unlike classical periodic comets, which can be observed over multiple passages around the Sun and for which extensive historical data have been accumulated, the object designated as the Triple Atlas is a unique case, as it has been discovered only once, and scientists have no opportunity to compare its behavior with previous manifestations. This makes its study considerably more challenging, as researchers are forced to rely solely on theoretical models based on knowledge of comets within our solar system. However, these models, although well tested for objects formed within our stellar neighborhood, may prove insufficiently accurate to fully describe the behavior of a comet formed in distant stellar systems beyond our galaxy. In an effort to understand the origin of this mysterious body, scientists undertake long and complex journeys back in time, tracing its trajectory across the galaxy to determine where it might have formed. Currently, the most probable hypothesis suggests that the comet originated somewhere within the so-called thin disk of the Milky Way, a flat, star-rich region where most star formation processes and planetary system formation occur. However, despite these assumptions, significant uncertainties remain regarding the accuracy of measurements of its current position and velocity, as well as the fact that these parameters, when traced backward through modeling, spread over time, leading to an increase in the size of the error regions. As a result, the ellipses representing possible origin areas become larger and more diffuse, encompassing numerous potential birth points within the galaxy. Understanding the galactic origin of the three Atlas objects is crucial for determining their chemical composition and age. Objects ejected from young stellar systems generally differ in their chemical signatures from those formed in older, more evolved stellar environments. For example, an abundance of carbon dioxide in the comet may serve as evidence of its formation in a protoplanetary disk, where temperature and chemical gradients differ from those present during the formation of the solar system. These differences allow scientists to infer the conditions under which the object formed, as well as its possible evolutionary history. Equally important is the structure of the comet, which sparks heated debate among scientists. One characteristic is the presence of massive cometary bodies and structures known as anti-tails, indicating intense gas emission from the nucleus. Such emission may suggest either a nucleus rich in volatile substances or a process of structural disintegration of the nucleus itself. Some experts hypothesize that the three Atlas objects could represent a loosely bound cluster of smaller bodies, a so-called rubble pile, held together by weak gravitational forces, which may weaken further and fragment under thermal or tidal stresses. At the same time, alternative hypotheses propose that this object is a monolithic structure with unusual surface properties or internal architecture, which in turn could explain the observed gas emission patterns. These differing models are important for predicting the comet's behavior as it approaches the Sun, especially at the point where gravitational and thermal effects peak, approximately 2 astronomical units from the star. In early September, the comet crossed this boundary, and observing its activity at that moment remains one of the most intriguing aspects. A sudden increase in gas emission could indicate the onset of sublimation of certain volatile compounds, which transition from solid to gaseous states at specific temperatures. Alternatively, this may indicate structural changes within the nucleus that have exposed previously hidden volatile materials buried beneath the surface, which now begin to sublimate under the influence of solar heat. Different volatile substances subliminate at varying distances from the Sun, creating a sequence of comet activation as it approaches perihelion. These processes help us understand how comets form and evolve. When it comes to the behavior of water ice in interstellar conditions, it is important to note that its intense gas release begins at approximately 3 astronomical units from the source, roughly 3 times the distance between Earth and the Sun. At the same time, carbon dioxide can remain active and subliminate at much greater distances from the star, far beyond where water ice becomes active. This difference is due to water molecules starting to evaporate intensively at higher temperatures, with their activity decreasing more rapidly as they move away from the heat source, whereas carbon dioxide can remain volatile at lower temperatures, maintaining its activity over considerable distances. The peculiar behavior observed in Comet 3I Atlas suggests the presence of a complex mixture of volatile substances, which activate at different temperatures. This means that its composition may include compounds with very different sublimation thresholds, a significant departure from the typical picture of comets known within the solar system. As a result, its behavior as it approaches the star and during periods of maximum solar heating may differ markedly from conventional scenarios, requiring more detailed analysis. However, observing this object presents challenges related to data gaps and the limited ability of Earth-based observations to monitor it during critical moments. It is especially important to note that many key tests of hypotheses regarding how the comet responds to intense solar heat occur under conditions where observations are hindered or impossible. In particular, when 3I Atlas reaches the point of conjunction with Earth at the end of November, scientists will need to interpret the results considering that the object may have undergone significant changes during its period out of view. Consequently, any alterations in its appearance, composition, or activity, potentially manifesting after the conjunction, will require researchers to revise existing models and theories. The appearance of the object after conjunction, as well as its behavior during this period, could either confirm current theoretical models or, conversely, reveal new mysteries that demand entirely different approaches and explanations. These situations exemplify the complexity of modern astronomy and astrophysics, as they involve extremely rare phenomena occurring under conditions that are as close as possible to the limits of our observational capabilities. Every measurement and observation contains an element of uncertainty, and every model is based on assumptions that ultimately require verification and confirmation. At the same time, all interpretations must consider the fact that interstellar objects may behave according to physical laws that have not yet been fully discovered or formulated, thanks to our experience studying the solar system. Before delving into hypotheses that go beyond conventional scientific explanations, it is essential to carefully examine simpler and more natural possible causes for the unusual behavior of 3I Atlas. In science, it is important first to rule out all familiar, albeit unusual, explanations that, despite their seemingly exotic nature, remain within the realm of known physical laws. Whatever happens around the comet, it likely still operates according to the laws of physics, albeit under conditions that are significantly beyond those we have previously observed. In this case, the comet's unusual properties are related to the fact that it exists under extreme temperatures and pressures previously inaccessible to human experience. The detected signs of carbon dioxide dominance in this object provide valuable insight into its nature, based on classical ideas about comets. Such composition indicates that it was formed in the region of its parent stellar system where temperatures were low enough for carbon dioxide to condense into a solid phase, that is, into ice. At the same time, water existed as vapor, characteristic of conditions where the temperature was above water's freezing point but still low enough to preserve water vapor. These conditions are typical for the region beyond the so-called carbon dioxide snowline, the boundary where temperatures are low enough for carbon dioxide to condense. Although our galaxy contains a variety of stellar systems, each has unique characteristics, especially regarding temperature profiles and chemical composition. These differences significantly influence the location of absorption lines, such as the carbon dioxide snowline, an important factor in the formation of comets and their orbital features. In particular, stars with lower temperatures compared to our Sun cause the carbon dioxide snowline to shift closer to the star itself. This means that in such systems, comets rich in carbon dioxide can form on orbits closer to the system's center than in our case. This effect allows objects rich in water ice to form in regions where, in our system, more water-rich bodies condense. In addition to this, there is a hypothesis suggesting that stars with a different chemical composition, for example, those richer in carbon relative to oxygen, may form protoplanetary disks where carbon dioxide formation dominates, regardless of the ambient temperature. This hypothesis helps explain not only the unusual chemistry observed in objects such as the 3ATSs but also their anomalous gas emissions. Since carbon dioxide sublimates at lower temperatures compared to water ice, this could theoretically lead to faster gas flows that exceed the velocities typical of comets, where water predominates. Such increased volatility likely contributes to the rapid brightening observed in September, as well as the extremely large size of the comet detected in the sphere. However, the abundance of carbon dioxide in the composition is only part of the explanation. To understand the appearance of an anti-tail directed toward the Sun, one must turn to plasma physics, which involves processes occurring at the intersection of solid mechanics, gas dynamics, and electromagnetic phenomena. When solar ultraviolet radiation ionizes the gases of the comet, a plasma forms, a mixture of electrically charged particles that respond to both gravitational forces and electromagnetic fields. The interaction of ionized gas with charged dust particles generates complex processes that can lead to the formation of self-organizing structures, which do not conform to traditional models of gravitational and radiative pressure. Charged dust particles can form streams, filaments, and even spiral structures under the influence of magnetic fields carried by the solar wind. Under certain conditions, these electromagnetic effects can overcome radiation pressure, allowing material to flow in directions previously thought impossible and even creating anti-tails directed toward the Sun, while normal tails extend away from it. This scenario is supported by observations, especially when analyzing the increased gas ejection velocities in conditions similar to those of the 3ATSs. Higher gas density promotes enhanced ionization and charge exchange processes, which can, in turn, amplify electromagnetic reactions. Furthermore, an unusual chemical composition, for example, an increased presence of molecules that ionize more easily or at different rates, affects plasma formation, making it more dynamic and complex. Another important aspect in explaining the anomalous behavior of such objects is rotation. The degree of their rotation and the associated mechanisms can serve as additional factors that, when applying known physical laws to extreme conditions, help elucidate their activity patterns and responses to the solar wind. As a result, all these factors, chemical composition, temperature, rotational dynamics, and electromagnetic interactions, combine to provide a comprehensive understanding of the unusual behavior of comets and their structures, which often astonish and sometimes even perplex observers. The mechanism of slow rotation of a nucleus in space can generate significant temperature differences between its day and night sides. These temperature gradients, in turn, promote the concentration of escaping gases in specific surface regions, as heat is unevenly distributed. When the rotation of such an object, tentatively called a 3-astronomical body, or simply 3 ATB, occurs slowly enough for its day side to heat up considerably more than that of comets moving within the solar system, an interesting effect arises. Thermal expansion and increased gas pressure in hot areas can lead to material ejections at velocities sufficient to overcome the radiation pressure directed toward the Sun. As a result, jets form on the surface of the nucleus, predominantly ejecting material toward the star, that is, in the direction of sunlight. with a strong concentration in the hottest regions. Justifying the hypothesis of slow rotation requires an explanation of why this occurs specifically with this object, rather than with typical comets, which rotate according to different scenarios. Interstellar objects traveling between various systems undergo diverse evolutionary processes. During their journeys, they encounter interstellar dust and particles, contributing to their gradual degradation and changes in physical state. Additionally, such objects experience gravitational torques caused by passing close to other stars, as well as interactions with magnetic fields, which can significantly influence their rotation. All these factors distinguish them from objects remaining within a single star system, where such external influences are minimal. A particular significance in examining this object is the appearance of green luminescence observed in September. This phenomenon presents a complex challenge for explanation based on natural processes. Typically, the green glow in a comet's coma is associated with the presence of diatomic carbon, which fluoresces under solar ultraviolet radiation. However, initial spectroscopic observations showed very weak presence of carbon-containing molecules other than carbon dioxide, complicating the interpretation. The threshold effect hypothesis suggests that the release of diatomic carbon became significant only when the object, tentatively designated as 3ATB, crossed a certain temperature or radiation threshold, which was approximately 2 astronomical units from the Sun. This means that as the star is approached, environmental conditions change so drastically that they activate chemical reactions previously unobserved. One possible mechanism is the photodissociation of carbon dioxide, that is, its breakdown under the influence of solar ultraviolet radiation into carbon monoxide and atomic oxygen. Subsequently, under further photodissociation, carbon monoxide could decompose, forming carbon atoms necessary for the creation of diatomic carbon. Such a process requires specific conditions, sufficient radiation intensity and molecular density, that may have been absent during the initial observations but developed as the comet approached the Sun's orbit. In addition, there is a hypothesis regarding the complex chemistry of carbon related to the formation of organic compounds. The core of the object may contain trace amounts of polycyclic aromatic hydrocarbons, amino acids, or other organic molecules, which under certain excitation conditions begin to fluoresce, emitting green light at longer wavelengths. This mechanism could also explain the appearance of green glow. Variations in the surface composition and internal structure of the object provide another possible explanation for the unusual behavior of the 3ATS. Instead of a homogeneous core, it may contain distinct regions differing in chemical composition. Some could be saturated with carbon dioxide, others covered with ice, and yet others containing complex organic materials. Such heterogeneity promotes the emergence of local effects. As the 3ALAS approaches the Sun and different areas of its surface begin to heat for the first time, complex processes are triggered that can lead to gradual changes in the composition and intensity of the gases emitted. In the initial moments of approaching the star, the dominance of carbon dioxide in the gas outflow may serve as evidence that the most volatile surface deposits, being the primary ones in this situation, are beginning to actively evaporate and leave the comet's core. These surface layers are the first to heat up, thus acting as the main source of gases during the early periods of activity. However, as heating continues and solar rays penetrate deeper into the subsurface layers, access to materials with different chemical compositions, often more resistant to heat, becomes possible. As a result, over time, the nature of gas emission changes, indicating the unveiling of new layers of the core previously hidden from external influence. The internal structure of the comet and its porosity are of particular importance, as they significantly affect the behavior of this celestial body. A highly porous core essentially represents a loose, porous mass composed of ice, dust, and small particles held together by weak cohesive forces. This structure allows solar heat to penetrate to significant depths, activating internal reservoirs of volatile substances that are usually isolated from external temperature variations. Thanks to the hypothesis of high porosity, it is possible to explain not only the extensive size of the comet itself but also its unusually rapid brightness changes. The deep heating of these internal layers promotes the evaporation of large volumes of volatile substances, which in turn causes intensified gas production, greatly exceeding the levels expected from simple surface heating. Evidence supporting this hypothesis is supplemented by assumptions that, during its long journey between star systems through interstellar space, the core's structure could have undergone substantial changes. Such transformations might have been caused by cosmic ray exposure, collisions with interstellar dust, or multiple thermal cycles occurring as the object passes through regions of increased radiation activity. These processes could have altered the internal properties of the core, making it more vulnerable and susceptible to subsequent solar heating, especially when the object enters zones of intense stellar radiation. The most plausible explanation for the unusual behavior of 3I Atlas lies in the combined effects of these processes, which occur simultaneously and interact with each other. The high content of carbon dioxide in the comet's composition enhances gas release, creating complex dynamic effects. Plasma-related physical phenomena form anti-tail structures and also cause a slowdown in the object's rotation. As a result, activity becomes concentrated in specific areas of the core, further complicating its behavior. At the same time, the complex chemical composition and interactions of chemical reactions led to changes in surface coloration, making it more diverse and constantly evolving. All these processes, although well studied within modern physics and chemistry, can produce phenomena that seem incredible and difficult to explain when they occur together under extreme conditions typical of encounters with intense stellar radiation. Comparing this comet's behavior to known objects in our solar system, one could say that 3I Atlas is more of an unusual and exotic phenomenon than something fundamentally extraterrestrial. However, it is precisely this unusualness and mystery that make it an object of special interest, as it has the potential to challenge existing notions about the physical properties of small bodies in the galaxy. Ultimately, such unique cases expand the boundaries of our knowledge and compel scientists to seek new explanations, sometimes even revising established theories. Moving on to the section dedicated to exotic and mysterious ideas, these concepts are, in essence, not strictly scientific hypotheses but rather mental experiments and reflections aimed at demonstrating how unusual and enigmatic our interstellar visitor is. They serve more as a kind of intellectual modeling, allowing us to understand possible scenarios and the hidden nature of this cosmic object, rather than confirmed scientific theories. In particular, the hypothesis of a lighthouse created with the help of extraterrestrial technology is considered one of the most popular and exotic explanations for the unusual characteristics of astronomical objects observed recently. Since the discovery of the so-called lone Oumuamua, which sparked heated debates and speculation about its possible artificial origin, each new interstellar object inevitably becomes the subject of fascinating conjecture. People begin to discuss potential technological signatures that could indicate the presence of advanced technologies in these cosmic travelers, beyond the reach of modern humanity. The rapid increase in brightness observed in the object designated with the tentative index, 3I ALS, along with its unusual structure, anti-tail, and enhanced coma, could, according to some researchers, be signs of activation of a certain automated system or device designed to respond to the radiation environment of star systems. Within the hypothesis of a lighthouse, Object 3I Atlas is considered a dormant technological artifact that has remained in a passive state for a long time, traveling between star systems. Such a device could conserve its energy and structural integrity, remaining inactive until encountering conditions that trigger its pre-programmed protocols. An increase in brightness in September, for example, might indicate that solar radiation has reached the necessary threshold to power these hidden systems. At the same time, the anti-tail structure that formed could represent directed energy emissions or material ejected into space for some technological purpose, either for communication or for protection. Nevertheless, this technological interpretation faces serious difficulties when attempting to reconcile it with the observed astronomical data. Spectroscopic studies conducted by the James Webb Space Telescope and ground-based observatories revealed clear signs of standard gases such as carbon dioxide, water vapor, and organic molecules, which fully correspond to typical comet spectra that naturally release gases. No signs of unusual isotopic ratios, artificially created materials, or energy signatures that could be linked to advanced technologies were detected. Some researchers also propose the hypothesis of a possible quasi-solid plasma, which they believe could explain the observed anomalies. This idea is based on theories about complex interactions in plasma environments that, under certain conditions, can exhibit patterns that appear organized. Laboratory experiments show that field plasma, a mixture of charged particles and tiny solid particles, can self-organize into structures whose properties resemble biological systems. These plasma formations can reproduce, evolve, and respond to environmental changes in a manner similar to living organisms, albeit in a primitive form. Some scientists suggest that such complex plasma systems could naturally occur in space, developing behaviors akin to those we associate with living beings. In particular, unusual gas emission patterns, anti-tail structures, and sudden increases in the brightness of an object conditionally referred to as triatlas, could theoretically be manifestations of these plasma phenomena. All of this provides fertile ground for speculation, but remains far from confirmed scientific facts and requires further research and observation to determine the true nature of the mysterious interstellar visitor. The concept of living plasma posits that interstellar space may be inhabited by unusual forms of matter organization that operate according to laws vastly different from those familiar to terrestrial biology and classical physics. These hypothetical entities might remain dormant during long interstellar journeys, showing no noticeable signs of activity. However, upon encountering electromagnetic environments, nearby stars, or magnetic fields, they could activate, producing effects that observers tend to interpret as signs of life or consciousness. In reality, such manifestations are more likely to mimic biological processes rather than being truly alive, and they require explanation through physical mechanisms that are still purely theoretical. Although plasma environments in laboratory conditions can form complex and stable structures, so-called plasma formations or clumps, the scaling of these phenomena to sizes comparable to comets or large cosmic objects operating within the solar wind exceeds current scientific understanding. Extrapolating such effects to cosmic scales, where interactions with interstellar or solar plasma occur over vast distances and under conditions very different from laboratory settings, involves assumptions that go far beyond established scientific data. Scientific observations and studies so far have not revealed any electromagnetic signals or signatures that could confirm the presence of large-scale plasma structures similar to those expected from organized, conscious forms of matter, hypothetically linked to an object known as the three-dimensional atlas, or 3I atlas. Within the hypothesis of target reconnaissance, the assumption that this cosmic object is an extraterrestrial satellite or reconnaissance craft, it is believed that it may be part of a mission undertaken from another star system. Such a scout would be programmed to study our solar system during its passage through the inner regions, and its unusual features, such as bright luminescence or specific structural characteristics, are interpreted as deliberate elements of its design. An extensive, very long comet, which may serve as a carrier of sensor detection systems or communication devices, could contain a special anti-tail region within its structure, functioning as a data transmission or radio communication link with remote receivers. In this hypothesis, the increase in brightness of the 3ATS, or three-dimensional atlas, is not accidental nor caused by simple heating of gases due to solar radiation, but represents a controlled activation of observation, communication, and data transmission systems as it approaches certain targets or research points within our system. The peak activity observed near Mars or during a flyby of perihelion, according to this version, is not a random reaction to solar heat but the result of pre-programmed protocols designed to conduct specific investigations. These scenarios suggest that the object wakes up or activates according to an internal plan or algorithm, making its behavior predictable and controllable. As a result, such observations can be interpreted as manifestations of conscious activity that awakens upon encountering radiation signatures or other signs of our star system, as if an artificial intelligence, long in a dormant state, suddenly becomes active. Some proponents of this idea suggest that the green coloration or color changes observed on the object's surface indicate the start of its sensors or sensory systems, which remain inactive until certain signals are received. Rapid changes in brightness, in turn, may point to processes of data processing and transmission, reminiscent of complex observation and communication systems embedded within this spacecraft. Nevertheless, the reconnaissance hypothesis faces the same challenge of verification as the hypothesis of its technological origin as a beacon or signaling device. Analysis of chemical composition, thermal behavior, and structural characteristics of the object. Modern theoretical physics suggests the existence of unusual forms of matter with exceptional properties, as well as the possibility of interaction with dark matter, alterations in the behavior of gravitational fields, and the manifestation of quantum effects on scales exceeding the familiar. These hypotheses open up prospects for scientists to explain phenomena that appear inexplicable or mysterious within the framework of standard physics. Such exotic phenomena could serve as keys to understanding the nature of the universe, expanding the boundaries of current knowledge and opening new horizons for research. The potential properties of unusual matter might, for example, explain the mysterious anti-tail observed in the trajectory of a cosmic object, attributed to so-called gravitational anomalies. These anomalies can distort the flow of matter, directing it in unexpected directions, thereby contributing to the formation and development of such unusual characteristics. Furthermore, these forms of matter could explain the enhanced emission of gases or ionized particles in the vicinity of cosmic objects, processes that go beyond conventional chemical mechanisms. In such cases, the energy required to release and accelerate gases could originate from mechanisms beyond known physical laws, such as unknown energy release processes or quantum effects. The rapid increase in brightness observed in some cosmic objects could also be related to exotic phase transitions or non-standard energy storage systems. Within modern physics, such phenomena demand new theories and discoveries, as they imply mechanisms that have yet to be identified or described by scientists. These hypothetical explanations suggest the existence of natural processes that significantly surpass current understandings of physics and imply that the hypothetical object known as the Tria Atlas is not the result of artificial technologies or human intervention. Instead, it could be a manifestation of natural processes based on physical laws that humanity has not yet encountered. In reality, this object might serve as a kind of laboratory where processes occur that are inaccessible for reproduction and study under terrestrial conditions. It presents a unique opportunity for science to observe the actions of physical principles that remain beyond our current comprehension. In this sense, it functions as a natural experiment, providing researchers with a chance to expand the boundaries of knowledge about the universe. Discussion of anomalies in time and spatial characteristics of such objects leads us into the most exotic and mysterious parts of modern science. The hypothesis that a hypothetical triad atlas could serve as a means of transmitting information or matter across cosmic timescales is an idea that gains particular development in science fiction. In such scenarios, the object is perceived not merely as a cosmic artifact but as a messenger or relic from the future, sent back in time using technologies that bypass conventional causality constraints. This assumption implies that the unusual properties of this object, such as its behavior or dynamics, could indicate temporal manipulation rather than spatial movement between star systems. In this case, the hypothetical object might be part of a future version of our own solar system, containing information or materials intended for our era. Its strange behavior results from interactions between future technologies and conditions existing today. However, scenarios based on temporal manipulation require highly complex physical principles, which to date remain unproven and contradict fundamental laws of causality and thermodynamics that govern modern physics. Currently, no observed data support the hypothesis of violations of conservation laws or the presence of temporal anomalies beyond the usual effects associated with relativistic phenomena at high velocities. The critical perspective on all these ideas is that often mysterious astronomical phenomena, which provoke numerous speculations and guesses, over time receive quite ordinary and logical explanations. For example, when pulsars were first discovered, the scientific community eventually understood them as rapidly rotating neutron stars emitting beams of electromagnetic radiation. History shows that any mysterious anomalies related to interstellar objects are eventually explained within the framework of existing physical laws, even if this requires considering previously unknown conditions or unusual processes. In the case of a comet whose characteristics surprised specialists, it is more likely a manifestation of extreme conditions typical of other star systems rather than evidence of new, exotic physics or artificially created technologies by intelligent beings. The main value of such research lies not so much in the probability of these phenomena existing but in how much they expand our understanding of possible scenarios and conditions that humanity might encounter in exploring the universe. An object capable of seriously prompting questions about extraterrestrial technologies, living plasma forms, or exotic matter is rightly considered a unique phenomenon, with no analogues within our current understanding of interstellar visitors. While the comet continues its covert journey through interstellar space, particularly through the perihelion region, these theoretical scenarios serve as an important reminder of how little we know about the structure and properties of the universe beyond our solar system. It remains uncertain how it will complete its voyage, whether it will become an ordinary, albeit unusual, object or continue to exhibit characteristics that challenge existing scientific concepts. In any case, its appearance has already significantly expanded the boundaries of our assumptions and theories regarding the nature of interstellar bodies. Part 15. The Countdown and its Implications. Cosmic clocks are relentlessly ticking, bringing us closer to a series of key moments that will not only reveal the properties and behavior of this interstellar object but also open new horizons in our understanding of a broader group of similar bodies drifting between the stars. Each subsequent stage becomes a crucial test for our observation methods, technological capabilities, and our ability to extract valuable scientific information from phenomena that go beyond current astronomical practices. The first of these critical moments will occur on October 23, 2025, when the comet will approach Mars at its closest distance, approximately 30 million kilometers. This encounter will present a unique opportunity for human observation of the interstellar traveler at a time when ground-based telescopes will begin to lose sight of it. During this period, orbiting spacecraft around Mars will attempt to conduct observations that were not previously planned within the scope of their original missions. These efforts will push technological boundaries and capture images and spectra of the object rushing through space at speeds characteristic of interstellar travel. The success of such observations depends entirely on numerous variables beyond human control. If the comet maintains or even increases its brightness, orbital instruments around Mars will be able to obtain detailed images of its structure, internal core, and motion dynamics, which are impossible to record with ground-based telescopes. Conversely, if the comet begins to fade after its peak in September, even the most sensitive space systems will only detect weak signals, insufficient for comprehensive scientific analysis. By the end of October, specifically on the 29th and 30th, at a distance of roughly 136 astronomical units from the Sun, a crucial yet hidden culmination point of this event will occur. It is then that we will have the opportunity to observe its movement and behavior during the so-called period of maximum approach, which could be a decisive moment in understanding the nature of this interstellar guest. In these fateful days for the object designated by the three atlases, it will face a test of its interaction with the solar system, as it enters a phase when the intensity of solar radiation reaches its peak. This period, critically important for understanding the comet's nature and behavior, promises to bring not only new insights but also the potential to radically alter our perception of how such celestial bodies respond to solar heating. The maximum heating, occurring during the approach, can activate volatile compounds that had remained stable throughout their interstellar journey. These compounds, hidden deep within the comet and resistant to dispersal, may begin to be released as powerful jets of gas and dust, creating phenomena sufficiently impressive to significantly change the fundamental physical characteristics of the object. As a result, perihelion, the point in the orbit where the comet is closest to the Sun, coincides with a moment when observers on Earth face particular difficulties. At this time, the comet is almost entirely obscured behind solar glare, and no existing ground-based telescopic system can penetrate the bright solar radiation to observe its state. This creates a cosmic paradox, precisely when scientific interest in the object reaches its peak, our ability to observe and study it diminishes considerably. All discoveries that could be made during this event will largely remain outside the reach of our instruments, forcing us to rely on indirect signs of the processes occurring inside. These indirect indicators, if they are preserved at all, will be valuable for subsequent analysis, allowing conclusions to be drawn about what is happening inside the comet despite the lack of direct observation. The observational deficit will last approximately 4 to 5 weeks, starting immediately after perihelion and extending until early November. During this time, the comet seems to vanish from the view of all existing systems, creating a sense of enforced silence within the scientific community. This silence is very important, as it is during this period that theoretical models predict the most active phase of its behavior, a phase that may include fragmentation, sudden brightness changes, chemical transformations, and other dynamic processes. Typically, such changes are accompanied by intensive observations from astronomical teams striving to capture all the nuances of this celestial body's behavior. However, this time, due to solar glare and technical limitations, observations will be extremely limited. The next significant event is the comet's reappearance in the field of view in early December. By then, solar wind and solar deviation will have reached such levels that ground-based telescopes will be able to detect and track the object once again, having passed behind the Sun. The visibility window will reopen, and the comet, which after disappearing in October could have appeared almost as a completely different object, will once again reveal itself. At this moment, it may show signs of fragmentation, sudden brightness changes, or alterations in its chemical composition, caused by its encounter with intense solar heating. These signs will allow scientists to gain new insights into the comet's internal structure and dynamics, as well as its chemical makeup. All these events related to perihelion expand our horizons of knowledge and provide opportunities for continued research even after its completion. The next stage is a possible collision or close passage near Jupiter, scheduled for March 2026. Although this event occurs at a much greater distance than the encounter with Mars, it offers unique opportunities for observing the comet. During this time, as it finally leaves the boundaries of the solar system, spacecraft such as Juno, or future missions like Europa Clipper, may record it with their observational systems. Depending on the position and orbital configurations, these remote observations could provide valuable information about the object's condition. What we can learn from these observations goes far beyond simply studying the comet itself. The analysis of interstellar chemistry, conducted as part of these studies, offers the chance to obtain samples of materials formed around other stars. Studying comet behavior and conditions beyond conventional understanding has the potential to radically change our comprehension of the complex mechanisms involved in the release of volatile substances and the dynamics of field grains, elements that play a crucial role in the formation and evolution of cometary bodies. Of particular importance is the study of the phenomenon known as anti-tail manifestation, which has recently raised serious doubts about existing ideas on how cometary materials respond to solar radiation. This phenomenon, appearing in the opposite direction to the usual tail of the comet, challenges fundamental assumptions about the properties and reactions of the substances that make up these celestial bodies and necessitates the development of new theoretical models. Such models must account for electromagnetic effects, which have been previously insufficiently addressed within classical approaches, opening new horizons for understanding the physics of comets and their interactions with the solar environment. The conclusions drawn from these studies also influence broader scientific questions related to populations of interstellar objects that occasionally cross the orbits of our system. These objects, known as interstellar visitors, could serve as key to understanding their role in the chemical evolution of the entire galaxy. In particular, the rare phenomenon of an interstellar body, Tri-Atlas, visiting Earth represents only the third recorded mission of this kind, confirming the hypothesis that many such objects originate from other star systems. However, its unusual characteristics indicate that the diversity of small bodies forming interstellar relics in our galaxy is much greater than current theoretical models predict. Each discovered interstellar object, especially considering the possibility of its disintegration or fragmentation, provides a unique opportunity to understand the internal structure and compositional gradients of such bodies. For example, if Tri-Atlas were to disintegrate during its passage through the solar system, it would become an unprecedented event capable of revealing internal layers and components of the object that were previously inaccessible for study. Fragments resulting from the disintegration could contain materials from different depths of the core, effectively allowing us to obtain samples from the formation of the object around another star. Analyzing the distribution of these fragments and their chemical composition will help uncover details of the internal structure that cannot be determined through observation of the whole, intact body. Equally important is the understanding that all research faces limitations related to the detectability of such objects, many of which remain on the edge of visibility even with modern technology. Regarding observational accessibility, it is most likely that Tri-Atlas will never become visible to the naked eye for Earth observers. Its peak brightness will probably remain at the level of the 11th or 12th magnitude, which is within the capabilities of current telescopes, but without specialized optical instruments, it will be impossible to see. The absence of a bright visual manifestation does not diminish the scientific value of such studies, however, it significantly limits the ability to attract public attention. Yet, it is precisely public interest and support that often contribute to continued funding in the development of astronomical programs. In the context of future research, an important event will be the mission planned by the European Space Agency, the spacecraft called Comet Interceptor, scheduled for launch in the late 2020s. This mission is revolutionary in its concept, as it is designed for rapid response to the appearance of recently discovered interstellar objects. Unlike traditional space expeditions, which require years of planning and preparation, Comet Interceptor will be stationed at the Earth-Sun Lagrange point L2 and will wait for the right target to appear. After this, it will be possible to quickly redirect for interception and detailed study of the object as it passes through the inner regions of the solar system. However, the capabilities of such missions remain limited, as a significant challenge is the timely detection of interstellar objects. The discovery of an interstellar object like 3I, Oumuamua occurred only a few months before its closest approach to the Sun, creating serious constraints on the preparation and implementation of a comprehensive scientific program for its investigation. This short timeframe does not allow for targeted and complex space missions aimed at a deeper study of this rare interstellar visitor. Even with modern rapid response systems, it is clear that future detection systems must be configured to identify interstellar objects years before they approach our solar system. Only then can sufficiently long periods be provided for thorough observation and the collection of the most complete information about such celestial bodies, significantly expanding scientific capabilities in the field of interstellar objects. To achieve this, it is necessary to improve ground-based survey and monitoring systems, as they represent the most promising and efficient means of expanding our knowledge. Among such initiatives is the construction of a large observatory named after Vera Rubin, which is currently being built in Chile and is expected to begin operations around the mid-2000s. This observatory will be equipped with unique capabilities for wide-area sky surveys, allowing for multiple images of large sections of the sky to be captured in short timeframes. With this approach, interstellar objects can be detected much earlier than their passage through Earth's orbit, providing scientists with extended periods for observation, analysis, and more detailed study of their characteristics. It is anticipated that the main scientific program, called the Rubin Legacy Survey of Space and Time, will focus on the systematic detection of interstellar objects at a rate of several per year after the full deployment and operation of the equipment. This sharp increase in discoveries will transform the study of interstellar bodies from incidental, individual observations into a comprehensive population study capable of answering key questions related to their origin, chemical evolution, and dynamics within the galaxy. Undoubtedly, this will be an important step toward understanding how interstellar objects form, evolve, and interact with their environment. Significant breakthroughs are occurring in the fields of adaptive optics, spectroscopy, and other methods of space observation, expanding our capabilities to study faint, rapidly moving, and extremely distant objects such as interstellar bodies of Type 3 Italian Lyras. The next generation of extremely large telescopes, such as the 30-meter telescope and the European Extremely Large Telescope, promises to provide incredible light-gathering power and high spatial resolution, which could revolutionize the characterization of interstellar objects. These instruments will enable the acquisition of clearer and more detailed images, as well as spectroscopic studies that reveal the chemical composition and physical properties of the detected bodies. The infrared capabilities of the James Webb Space Telescope have already demonstrated their high value for studying interstellar objects, providing unique data on their chemical makeup and physical state that were impossible to obtain with previous generations of instruments. In the future, launches of new space observatories specifically aimed at monitoring small bodies are planned, allowing for continuous observations regardless of Earth's atmospheric conditions or solar conjunction periods. These systems will open new horizons for long-term and comprehensive studies of interstellar objects. International cooperation plays a crucial role in this process, as the study of interstellar objects requires coordinated efforts on a global scale. Joint observational campaigns enable monitoring across different parts of the world and time zones, significantly increasing the efficiency of discovering and researching new cosmic bodies. The experience gained during the implementation of the 3IATLC project has demonstrated both the potential and the challenges of organizing a global response to rapidly changing astronomical events. This knowledge and these skills will serve as a foundation for developing effective protocols and data processing standards, as well as for accelerating the scientific community's response to new discoveries. Data exchange methods are becoming increasingly important due to the accelerating detection of interstellar objects and the growing opportunities for joint research. The development and implementation of specialized protocols are essential, as these standards and procedures will undoubtedly become indispensable tools for scientists and research teams. With each new discovery, the need for coordinated actions and information sharing increases. At the same time, the deeper and broader implications of such observations extend beyond pure astronomy, touching on fundamental questions regarding the nature of matter and the chemical composition existing throughout our galaxy. In this context, the so-called three atlases take on particular significance, a unique research project that provides direct physical evidence of conditions that existed in other star systems. These data have been preserved in their pristine form because interstellar objects, traveling for millions of years, maintained their original characteristics, allowing scientists to glimpse the conditions that existed in the distant past and could serve as a key to understanding the origins of planets and other celestial bodies. Each new measurement conducted within this project makes an important contribution to expanding our knowledge of how planetary formation processes differ across various types of stellar environments and conditions. Research into interstellar objects also raises questions related to astrobiology, as such bodies could transport organic compounds or even primitive forms of life through interstellar space. Although there is currently no direct evidence of biological materials in interstellar bodies, analyzing their organic chemistry can provide valuable information about the distribution of complex carbon compounds throughout the galaxy. The detection of amino acids, nucleic acids, or other prebiotic substances in interstellar objects could radically alter our understanding of how the chemical components of life spread and become established in space. While the chemistry characteristic of the three atlases is not directly biological, it demonstrates that interstellar bodies are capable of preserving complex molecular structures even across vast galactic distances. An important area related to the study of interstellar objects is planetary defense. Although this topic is not directly part of the three atlases project's objectives, the results of research into interstellar bodies and their characteristics enable more accurate predictions of the behavior of potential hazardous objects, especially those that could approach Earth. In particular, studying their trajectories, responses to solar heating, and other physical processes helps improve forecasting and risk assessment systems for collisions. The behavior of interstellar bodies reveals limitations in existing models used to predict the dynamics of comets and asteroids, highlighting the need to consider objects that do not conform to traditional notions of the solar system in planetary protection efforts. A deep understanding of the physical processes occurring with interstellar bodies is becoming crucial for accurately assessing potential threats and developing effective measures to neutralize them. The possibility of engaging with the public in the context of interstellar object research, such as the three atlases, simultaneously presents both a challenge and an advantage. The technical complexity of such objects, their low visibility, and rarity make them difficult for the average observer to access, creating barriers to widespread public interest. However, the unique origin of these bodies from interstellar space, as well as their unusual and sometimes astonishing characteristics, generate keen interest among those who understand their significance for science and humanity's future. Educational institutions around the world actively incorporate practical exercises and lessons related to observing such objects, transforming them into living examples of modern scientific discoveries. Students have the opportunity to independently observe comets and interstellar bodies, analyze available data, and witness how our understanding of space evolves as new evidence emerges. This approach fosters a deeper and more engaging perception of science, stimulates curiosity, and broadens the horizons of knowledge for young scientists and enthusiasts. The commercial space industry has recently shown increasing interest in studying small celestial bodies such as asteroids and comets. This interest is driven not only by the scientific value hidden in the mysteries and features of these objects but also by the vast potential for economic activities related to their characteristics and resources. Within this trend, particular emphasis is placed on researching small bodies capable of becoming sources of valuable materials, opening promising prospects for future space mining. However, despite the fact that some of these space objects, such as the three ATCs, are not intended for resource extraction or mineral mining due to their hyperbolic trajectories, the methods developed for their study significantly expand our capabilities in characterizing and understanding small bodies. These developments allow us to obtain crucial information about their composition, structure, and behavior, which could serve as a foundation for more successful and efficient space missions aimed at commercial exploitation in the future. As certain critical dates in October approach, the space object known as the three ATCs has repeatedly demonstrated that interstellar visitors like it continually challenge our existing notions of human capacity to comprehend the universe. Its appearance in our system shows that the boundaries of what we consider possible in space beyond our solar system are increasingly blurred. This object has become a vivid reminder that the universe is full of unexpected discoveries capable of changing our perspective on the world around us. Whether future behavior of this cometary body confirms existing theories or presents entirely new mysteries, it has already set a new standard. Even the most unpredictable and extraordinary astronomical phenomena can manifest in our reality. The final assessment of the heritage of the three ATCs will depend on the data we receive in the coming weeks, as all efforts by scientists and research organizations are focused on observing this cosmic visitor. A crucial aspect of understanding this object is that it represents something more than just another space rock passing by. It is beginning to reveal itself as something unique, a chemical time capsule brought from another star, or perhaps a physical laboratory operating under conditions previously inaccessible to humans. It is entirely possible that it is something even more extraordinary, forcing us to completely reevaluate our notions of what wanders through space between the stars. In the next few weeks, the three ATCs will either shine brightly, illuminating everything around them with a dazzling glow, or disintegrate into numerous interstellar fragments, scattering into cosmic dust, or quietly slip past our sun, carrying its secrets back into the infinite darkness of the universe. All this uncertainty and the potential scenarios will alter our perception of such interstellar visitors and their role in the cosmic expanse. This calls for all interested and curious parties, scientists, engineers, astronomers, and simply enthusiasts, to closely monitor the developments. It is important to follow the publication of images and data obtained through missions such as MS Express and Trace Gas Orbit, conducted by the International Space Agency, as well as the results of research carried out by NASA using the MS Reconnaissance Orbit and MAVEN spacecraft. Subsequently, we should expect new updates from powerful tools like the Hubble Space Telescope and the James Webb Space Telescope, which may reveal the true nature of this mysterious cosmic object and provide answers regarding its composition and origin. Ultimately, the universe has sent us a messenger from another star, and we are now on the verge of deciphering this message. For the scientific and human community, this is a unique opportunity to understand what exactly this message carries and what significance it holds for our entire planetary civilization. These upcoming weeks will be crucial for obtaining new insights.